iJulia. Then using iJulia and using the notebook command will launch the notebooks in a browser. And then you switch over to the browser to use the notebooks. Oh yeah, you also have to CD into the. Okay, great. And so for the format of this, we will also take breaks in between the individual notebooks to give you some time to get some water or keep your sanity.
Keep ours.
Yeah, also for ourselves. Great. So assuming that you've got the notebooks done, and the rest of this talk does not rely on you having the notebooks. So you can figure that out over the next couple minutes. So I wanted to just go over, I have all the chats and stuff opened up. Let me close this. So I wanted to go over just from ground zero, what is a graph, right? Why do we care about graph theory? Why is this area of mathematics interesting? And why do we care so much about computing with them? And the reason is generality. So going back all the way to the time of Euler, there was this question: if you live in this town, Königsberg, can you cross all of the bridges once and see the whole city? So very initially, graph theory was tied to the question of navigation on a map. And really, the idea here is that it doesn't matter where the bridges are located in space. The only thing that matters is the connectivity pattern, is which islands. So there's an island in this river, and then I guess there's two islands in this river, and two banks of the river in this town. Never been to this town. So the question was, can you go to all of the islands, all the land masses, by crossing each bridge once? And in order to answer that question, Euler kind of spawned graph theory. And then, of course, graph theory had its renaissance in the early part of the 20th century, middle part of the 20th century. So you can abstract this map question to a set of vertices, here shown in black dots, and edges shown in gray lines. And then, oh, I missed a blue line. Should be a blue line here too. Okay. What is a graph? It's exactly characterized by this. You have a set of vertices, V, and a set of edges, E, and two functions from the edge set into the vertex set. So every edge has a source vertex, and every edge has a destination vertex. And we can draw these as directed graphs, where vertices are shown with black dots, and edges are shown with gray arrows. And in a directed graph, the edges have an orientation. There's a source vertex and a destination vertex. A lot of graph theory is done in the setting of undirected graphs, which LightGraphs defaults to just calling graphs, and we call digraphs the special ones. So in an undirected graph, you have the same setup: an edge set, a vertex set. Every edge has a source vertex, and every edge has a destination vertex. But you can reverse edges. So every edge is reversible, meaning there's kind of another edge that is the edge whose destination is the source of the one you started with, and whose source is the destination. So you can always flip the source and destination of every edge. And when we draw undirected graphs, we don't orient the edges. The way this is stored in LightGraphs is that we order the vertices 1 through n, where n is the number of vertices. And then an edge is stored as as a pair of the source vertex and the edge and the destination vertex. So here we now have to number the vertices, and then we store the edge set. You can store the edge set as just a list of these pairs. Problem with storing it as a list of pairs is that it's unindexed. And so if you want to know what are all the edges incident to vertex 3 here, in the edge list, you have to navigate is this an edge incident to 3? Is this an edge incident to 3? Yes. Is this an edge incident to 3? Yes. Is this an edge incident to 3? Yes. Is this an edge incident to 3? No. So it takes linear time to find the edges incident to a vertex. So we index them into adjacency lists, where you store for every edge for every vertex, you store a list of tuples. We'll get more into how graphs are laid out, why they're laid out that way, and different ways of laying them out later in the tutorial. Great. So graph theory is intimately connected to linear algebra, and linear algebra being the workhorse of modern mathematics. You're probably familiar with linear algebra from school. And so the way you get from graphs to matrices is through something called the adjacency matrix. So the adjacency matrix A is indexed by the vertex set on both sides. So Aij is 1 if there's an edge from Vi to Vj. Otherwise, it's 0. And the adjacency matrix is a cool little gadget, mathematical gadget. You can count paths in the graph by doing matrix multiplication. So that if you take the adjacency matrix and you multiply it by itself, so the adjacency matrix itself describes, is there a path of length 1 from I to j? The square of the adjacency matrix is there a path, or sorry, how many paths are there from I to j? Is the ijth entry of the kth power of the adjacency matrix. So you can use linear algebra to do graph theory. And you can, not only can you use linear algebra to compute things in graph theory, you can use linear algebra to define computations that you want to do. So you might have heard of this website called Google. It allows you to find information on the internet. And the original tool for how you found information on the internet using the search engine was a linear algebraic technique called PageRank, which is defined as solving a linear system in terms of the adjacency matrix of the graph, where that graph is the vertices represent web pages and edges represent links from one page to another. So you store the internet as a graph, you then construct the adjacency matrix of that graph, you plug that adjacency matrix into this linear system, and you solve a system of linear equations to know what pages should be highly ranked in search results. Now, it's more than 20-year-old technology, so that's not how they do it anymore, but it's a classic result in computational graph theory. So there are lots of other places that graphs show up, including transit networks, like a metro map. So again, how can I get from the airport to the central business district or to the museum I want to go to? What's the shortest path between these two places, given the metro network? So power grids are another aspect. This is the power grid of Florida, which is where I live. And there are structures. You can see how the power grid infrastructure corresponds to how people live in the region where the power grid serves. And graph theoretic questions about what paths exist, how many paths exist, the centrality of various vertices, answer questions about where power failures are likely to occur, power outages. How do power outages cascade through the system, where a small failure of a single part can lead to a large failure of the grid. We also look at social networks and how people are connected. Very similar ideas of like social media influencers and how information cascades throughout the graph. Clusters for finding groups of people who are more tightly connected to each other than they would be expected under a kind of a null hypothesis. And then knowledge graphs, where you're storing human knowledge in a data structure. Graphs have this ability to capture both very highly structured information and very unstructured information. Depending on how you set up your vertices and edges, you can end up with graphs of very different structures. And so knowledge graphs are, you can ask questions about the graph where vertices are concepts and edges are relations between those concepts, can allow you to do logical deduction and reasoning over the corpus of knowledge in your knowledge graph. Another fun example is you can analyze sports with graph theory. So for a while, college football was ranked. So you play all the college football games in the US. And at the end of the season, there was something very similar to PageRank that was used to determine which two teams should be in the final championship for the national championship. And so that graph theoretic analysis, which again went through linear algebra, you form a graph and then you form a matrix based on that graph. Then you solve a system of equations on that matrix. So the graph theoretical questions were used to understand and decide questions about sports. So here are a bunch of different things you can do with graphs, and they're all about finding structure in complex data. Showing here in this visualization, identifying clusters, and these clusters are regional. They're dictated by the spatial layout of the colleges, and it can be inferred, the spatial layout of the colleges can be inferred from the set of games that they play, because teams play games more frequently with schools that are closer to them. So then there's lots of complex graphs in science. If you're at JuliaCon, you're probably doing some kind of technical computing where you're doing electrical engineering or signal processing or physics. There's another tutorial I'll cross-advertise for David Sanders' tutorial on learning epidemiology and Julia simultaneously, making epidemiological models for modeling if you wanted to model a coronavirus, you could get started in Julia, and he's showing lots of models of increasing complexity and increasing computation. So after this tutorial, you should watch David's tutorial on learning Julia through epidemiology. So I think I wanted to continue on that thread where all of these different aspects of computer science all rely on graphs. So in probability theory, we have Bayesian networks, which are used in statistics and machine learning. We have neural networks and deep learning, it's a technique in machine learning. And this also uses a graph where the vertices represent features of your data, and the edges represent this computation depends on this data. In the Bayesian network context, the variables represent covariates, and the edges represent causal dependencies between covariates. So it's a model of causal statistical processes. In optimization problems, you can think of like linear programs as a bipartite graph between the constraints and the variables that participate in those constraints. So there's an edge from you have some set of constraints, you have some set of variables, and there's an edge from the constraint to the variable, and the weight on that edge is the coefficient in that linear constraint. Markov decision processes have kind of a stochastic finite state machine approach, where you have states that the system can be in, and in any state, the system can transition to another state. This can also be represented by a bipartite graph on state. One set of vertices are states, another set of vertices are transitions, and edges represent that a state, from this state, you can participate in this transition, or from this transition, you can go to a state. Chemical Petri nets are designed for capturing the law of mass action of chemical reactions and compartmental models in epidemiology, something I've been studying recently. And these also can be represented as bipartite graphs. Then database schemas are also graphs where you have tables and foreign key relations. and a table is connected to another table if there's a foreign key relation there. So make files, if you've ever compiled software, you've interacted with the make tool, and you can, what it does is build dependency graphs where the vertices are things you want to compile, and the edges represent that, sorry, the vertices are tasks you want to execute, and the edges represent dependencies that I can't do this task until I have done all of my parent tasks. And then in cybersecurity and computer networking, we can analyze computer networks as you have vertices for clients and vertices for servers, and edges represent flows of traffic from machine to machine. So questions about the graph correspond to questions about what's the maximum bandwidth, what's the expected latency, how can we route packets through the network. So all of these aspects of computer science can be answered with tools of graph theory. So LightGraphs makes a couple assumptions about what is a graph. We assume that vertices are integer, that the vertex set is contiguous, that in any graph, it is either directed or undirected. You can't have, in some statistical tools, they use mixed graphs, where some edges are oriented and some edges are not. So that's not allowed in LightGraphs. We don't represent multi-edges. And self-loops are given kind of a second-class status. So you can have self-loops, but it's not guaranteed that every algorithm will be correct in the presence of self-loops. So I try to stay away from self-loops. But if you really need to use self-loops in your application area, then you should raise issues when you find bugs. Yeah, and this is an artifact of kind of implementation simplicity. So when Seth and I were getting started on LightGraphs, it was all about just the basic stuff. There was no parameterized types. This was back in like Julia 0.2. So there were a lot of limitations from the compiler that are no longer limitations. So some of this stuff, like the code is not as generic as it could be. And that's an artifact of that level of generality. That level of generality wasn't available back then. Like we didn't have name tuples until very recently in the history of Julia. If we had name tuples back in the day, we probably would have supported metadata better in general. Okay, so you can't have, so some things that people like are kind of sparse vertex sets where you just have like vertices with random names that aren't into contiguous integer labels. Like you might want your vertex set to be 1, 2, 3, 4, 7, the string name, and 1/3. And LightGraphs isn't going to let you do that. There's another package that we will talk about today, also maintained in the JuliaGraphs organization, called MetaGraphs, which supports a lot of those features. So you can have, in a metagraph, every edge or vertex can have a property, which can be basically any Julia type. And you can think of that as that property is a tuple. Like if you want multiple properties on the same vertex, you have as your property a tuple whose fields are the different types of metadata. So this you can use to give kind of shapes to the vertices, give them names. You can put weights on the edges, multi-edges way by having a number there or a list of edges on that edge. Anyway, so graphs. Yeah. So the next thing is benchmarks. Timothy Lin put together some benchmarks of all these different graph packages, X, which is Python, Network Kit, iGraph, Graph Tool, LightGraphs. And I'm fairly confident that Network X are the only tools 100% high-level language. Snap, iGraph, Network Kit, and Graph Tool for iGraph and GraphTool and Snap, but have C, C++, or in function interface stuff. So like there's a R interface to these two, R or Python interface to iGraph, and you Python, but all of the graph computation that you write is actually like in NumPy, a runtime that's implemented in a low-level language. So NetworkX and LightGraphs are 100% in their high-level language. NetworkX is in Python and LightGraphs is in Julia. Okay, so Tim Lin made these benchmarks. Seth tuned the LightGraph versions because he was unsatisfied with our performance. And we're not the fastest on every task. Here are the benchmark results. And other than loading the graph from disk, we are the fastest. So for shortest path, PageRank, K-core, and connected components, LightGraphs is faster than, or I guess GraphTool is faster on connected components, but I'd call this difference marginal at best. So we're doing really well, keeping in mind that LightGraphs is purely in the high-level language Julia. So what this tells me is, one, we're doing great on having high-performance graph algorithms, and two, we need to invest some more time in loading the data. So this is the same data presented in table form, and you can see that for things like PageRank and K-core, we're hundreds of times faster than NetworkX. And 10 times faster than the next competitor on some of these things. So, great. And then those benchmarks also showed that LightGraphs can scale with parallel threads. Our single core performance is so good that you actually need a lot of threads to outpace the single core. So here, if you have 8 threads on your machine, that's break even with serial, because the serial algorithms are more efficient in the first place. But after 8 threads, you start to see performance gains by going to 16 cores. And then you can also see that our times, our times in general are much shorter than the GraphTool and the NetworkKit times. Great. So again, here are the pictures of your hosts. We're all, I think, showing our video on the Zoom. Be active in your asking the questions.
Yeah, so there was one question that that was answered quickly, but is CatLab designing a multi-graph type of structure with multiple edges between 2 given vertices?
Yeah, so who asked that?
I think it was lost somewhere in the chat.
Oh, okay. Yeah, so my recent project in the algebraic Julia ecosystem, including a package called CatLab.jl, is working on putting these graph applications on a more mathematical footing, a more consistent and homogeneous perspective on all these different ways you can use graphs. And one of the things it has is true multi-graph support. When you kind of change, we developed LightGraphs in the same way that graph theory is presented in an undergraduate graph theory course or a graduate school graph theory course, where you start from simple graphs, no loops, no multi-edges, no weights, and you kind of go through everything, and then you say, okay, well, which of these properties generalize to graphs that have loops or graphs that have weights or graphs that have multi-edges? And that's a very standard way to do it, because that's the standard university math education, computer science education as well. But we really should, if we're doing it over again, we would take weighted multi-graphs with arbitrary metadata as the starting point, and start from there. So yeah, I think that will. I have another talk at this JuliaCon that's been pre-recorded and will be played next week that talks about that.
Mm-hmm.
Great.
All right. So do we still have questions here? I assume you can have graphs with disconnected components and isolated nodes from.
Yes.
Yeah.
Yeah. So you can have isolated nodes, meaning vertices that do not have any incident edges to them.
Mm-hmm.
You can have disconnected components, meaning, I guess we haven't defined connected components yet, but there are these equivalence classes that you put on vertex set that respect the edges. So you can have isolated vertices and disconnected components. What you can't have is vertices that exist with a higher vertex number than vertices that don't exist. So if you have vertex 7, you have to have vertex 6. It can be disconnected. It can have no incident edges, but it has to exist. And then you can index your you can index your vertices with any subtype of integer. So if you have, like in chemistry applications, if you're storing, say, organic molecules, you might, if you were building a database of organic molecules, you'd have a lot of very small graphs where each graph had, say, less than 16 vertices or less than 32 vertices. So you don't want to use a 64-bit integer to store each vertex if you only have 4 bits or 8 bits or 16 bits worth of vertices. So that's one of the reasons why LightGraphs supports arbitrary integers for indexing. But it's an order of magnitude, and it was a lot of complexity introduced into the code base when we were adding that. Now we're used to it and we don't think about it that much, but there's a lot of work when we went from assuming everything was the native machine int, whatever native machine int you were on, right? If you're on 32-bit or 64-bit machine, you got 32-bit or 64-bit ints. But going from that to thinking, okay, well, every algorithm has to work for every int type.
Mm-hmm.
And so then you get hard questions like, okay, if I have if I'm using int 8 as my vertex type, and I have the maximum, 2 to the 8 vertices, and I add a vertex, what do I do? Do I error because I don't have enough room to store that vertex type? Or do I convert my graph up to int 16s and change everything, and recode the edges? So yeah, that was a lot of work. Making it work for arbitrary types, like arbitrary vertex types, would be the approach we took was to use MetaGraphs, where you attach that information onto integer labeled vertices. This might be a very detailed conversation for people for the intro of the tutorial. But
somebody was asking about the benchmark too. So about this, this bump we have compared to the other libraries. So how come the serial is really good compared to the 2 threads?
Right. So we do not run the parallel algorithm with 1 thread. We use a different implementation for the multi-thread. I mean, that's the right way to do parallel computing benchmarks, is to use the fastest available serial algorithm and then the fastest available parallel algorithm. You're not supposed to take the parallel algorithm running with 1 thread as your serial comparator. So I don't know enough about how the other graphs are doing it, but that's indicative. When you see that like 2 threads is faster than 1 thread, usually it's because your single-threaded algorithm is the same algorithm just run with 1 thread. You're not taking it. You're not exploiting that serialism. You're not exploiting the serialism to use a fancier data structure or something. That's my gut from my experience in doing parallel computing. That's usually what that indicates. How can we attach? So yeah, so we'll talk about in the third notebook. I see a question, how can we attach weights to edges? And that'll be in the simple weighted graphs. Great. So I think at this point, Matt, you should take over the screen share and we'll move on to your notebook.
Yeah, sure. So there's still a bunch of unanswered questions, but I think some of them will come afterwards when we get onto the corresponding notebooks. Right. So we'll now get on, do you all see the screen correctly, the notebook? Right. So yeah, we'll start with the second part, or yeah, we'll continue with the second part, which is SimpleGraphs and SimpleDiagraph, which are the Swiss Army knives of the same default that you would always think of using first for defining graphs or working with graphs in general. And then when you see that you need something specific or you want to tune performance for some specific properties, then you would consider some other graph types. But these two are basically the ones you always think of to get started on some application. Right. So they're also the first graph types that were defined in LightGraphs. So it was, well, what is a graph? And basically, historically, a graph was what the idea of these simple graphs and SimpleDiagraph were. So it's basically an adjacency list wrapped in a custom type that has some specific methods exposed to it. So yeah, we'll get started and we'll just be using LightGraphs here and GraphPlot. I won't be explaining much about plotting graphs because Simon will be doing it right after on the fourth notebook. So we'll just be displaying here. Oops, I'm at 17, but trust me, I'm not cheating, so you can restart from 0 here. Right, so what I can do here is basically define a graph. So this will create for me a specific type of complete bipartite graph. So I have 2 parts with 2 nodes each. So I have the nodes 1 and 2 and the nodes 3 and 4. And each node of each partite is connected to all nodes of the other partite, which means that 1 will be connected to 3 and 4, 2 will be connected to 3 and 4, and then 3 and 4 are only connected to 1 and 2. Okay, so I wanted to show you this so we mentioned adjacency lists. And so the adjacency list for this one will be this structure here. So if you take the textbook definition of an adjacency list, it's an ordered list of unordered collections. So the outer list here is ordered and each index corresponds to the vertex. So vertex 1, 2, 3, and 4. And then the inner collections correspond to the neighbors of this vertex. So the vertex of 1 would be 3 and 4, vertex of 2 would be 3 and 4, and so on. So that would be the textbook definition, or what you can find in graph theory books on what an adjacency list would be. If we look at the adjacency list of this graph here, it's roughly the same structure with some few particularities. First one is, so we're not using a list, we're using a vector here, but this will usually be a good default to have, especially in Julia. So with vectors being a fairly same default to have for most of the operations you're doing. And then the inner collections, more interestingly, are not unordered collections, but are also vectors. And more specifically, they are sorted vectors. And so we can find vertices more quickly in that setting. So instead of having a list of sets, we have here a vector of vector. One other motivations for this is vectors are lighter in memory and faster for lots of operations. So here, if you take the summary of size, so this is basically giving you how much memory does it cost to store something, some object. And if I take some empty vector of integers, it takes me 40 bytes and 336 for sets of int. So if you had this notion of a simplest notion of unordered collection here. So this means we can make LightGraph way faster with these fairly simple data structures. Right. The other surprise you might have, and James mentioned it already, is redundancy. So if you look at it here, you could say this is not that efficient because each edge will be stored twice. So remember here, for example, this edge from 1 to 3, you are storing it once by adding 3 in the vertex 1, and then you're storing it twice by adding 1 in the vertex 3 here. So the information of each edge is added twice to this adjacency list. So you could think of it as a redundancy, but it makes operations way faster, and just adding an integer to a list is not that costly overall. So you could compare this. So another point of comparison could be dictionaries or sparse matrices. But dictionaries are usually slower, and they cost a lot more memory, and they have a huge memory overhead. So even creating small graphs, which would be quite a cost. And sparse matrices are used in some cases for some specific graphs, but in general, removing a vertex will mean deleting a row and deleting a column of the matrix. And if you're doing so, then you have to recreate the matrix from scratch, which can be very expensive, especially when you're deleting or adding vertices quite often. Right. So SimpleGraphs scales fairly well. So here you have the creation of a simple graph 3 times with different number of vertices. So we're creating with 0 edges and different number of vertices, and this is usually fairly fast if my machine is willing today. But yeah, it's because it's basically creating an empty vector of vectors. So it's allocating each vector once, but this is fairly fast compared to other operations such as instantiating a dictionary. Yeah, my laptop might not be liking having Zoom and Jupyter in parallel, but yeah. So you see the time here, even for creating large empty graphs, this remains fairly reasonable in terms of time. And because of this adjacency structure, SimpleGraphs and SimpleDiagraph make it easy to create large sparse graphs very easily. So creating empty graphs costs almost nothing, and then adding edges is just pushing 2 values on 2 vectors, which is also fairly cheap. But on the other hand, if I create complete graphs, so that would be almost the worst case for creating a simple graph or simple diagraph, this will be a bit slower, and this will not, well, this will cost more memory and more time when creating it, but still quite reasonable. So 1 millisecond in that case, in the worst case, with 1,000 vertices here. Right. So we talked about undirected graphs up to here. What about directed graph? So when the edges now have a sense, a direction from one vertex to the other, and not just a connection between 2 vertices. So here I created a complete diagraph. So we have 5 vertices, and they're all connected with each other in all senses. The only edges we don't have here are self-loops again. So how are these stored? Well, again, you could, just like James mentioned, we could have just a forward pass, so the forward list, saying for each vertex, we store the vertices it points to. But if we have only this, then some algorithms will be awfully slow, because sometimes you need to start from the end of some path and go backward. And if you have to do that, then you have linear time just to access the neighbors that point to a vertices, and then you access again all the vertices to see which point to another vertex. And so in that case, you would end up being catastrophic for some algorithms and fast for some others. So the solution for that is to store the list twice. So you store a forward list, or a list of forward edges. So for each vertex, you store which vertices it points to. And then you have this backward list where you store for each vertex which other vertices are pointing to it. So in that case, I will create another directed graph here, a simple one, which will be a cycle. So from 1 to 2, 2 to 3, 3 to 4, 4 to 1. And then I will just check what do the 2 structures look like. So it's basically storing the 2 structures separately. First one will be the forward list. So for the vertex 1, we are pointing onto 2 unique only, and so on. And then the backward list will be exactly the opposite. So the vertex 1 is pointed onto by the vertex 4 only, and so on. And so this means when we add an edge, we have to add it to the 2 lists at the same time, and we keep the 2 lists synchronized. Right, so we can construct simple graphs from different manner. I'm not going to present all of them, but it's just to show you that you have some flexibility in the way you construct your graph, because depending on your application, you might get your initial data in different forms. So our first one is, well, I have to define a graph from scratch, and I just define it with my custom integer type like this. And so this will just create my graph with these 0 vertices, 0 edges, and my custom type, which I can change. So as we mentioned, if we have smaller graphs, it might be interesting to use this uint8 for vertices, for vertex types, and so on. As mentioned, graphs are basically matrices with some special semantics. And so we can also create graphs from matrices directly. So here you have the adjacency matrix that we mentioned before. And this is for a directed graph. So it means if you take the entry ij, so with I being the row and j the column, then this would be 1 if there's an edge from the vertex I to j, and this would be 0 otherwise. And so I would just plot directly a simple digraph that's created from this matrix here. And this gives me this graph there. And so this is fairly useful if you have the matrix already defined. You don't have to loop over the entries of a matrix to check is it 0 or 1 and then add manually. You can just pass the matrix. Sometimes you will have not a matrix, but a list of edges, and that can happen quite a lot. And if you have your vector of edges, you can also create your graph directly from it, and this will basically iterate over your edges here and add them to the list, to the adjacency lists. So here I'm just creating a simple graph, so non-directed this time, with edges from 1 to 2, from 1 to 3, and from 3 to 3. So here I'm adding a self loop, and well, this does not break anything. I didn't make my computer crash. Don't try that with all the algorithms, but it will mostly work. And so yeah, so I can create from this vector of edges my graph and plot it directly, and I get this one. So the only edge you don't see here is this self loop on 3, which corresponds to this edge there. Right. Sometimes, so if you know a bit about Julia, you know that creating a vector is sometimes not that useful, and you can just avoid creating it altogether if the only thing you're doing on it is iterating. So instead of creating graphs from a vector of edges, you can create it from an iterator of edges. So something that you can iterate over and that you can pull data from one iteration at a time. So here, instead of using the square brackets for creating a vector, I will use this parentheses, which will create a generator. So this will define a structure that I can iterate over, and this will create edges one at a time. So I could have 1,000 here, and this will not allocate a vector of 1,000 entries. This will just define an iterator that I can iterate over 1,000 times. And from this one, I have this special constructor here, which is SimpleGraph from iterator, and I pass it my iterator, and it will just loop through it until the iterator is done and add the corresponding edges. And yeah, and here we go. So again, it really depends on what your incoming data looks like. If you already have a full matrix, you don't need to convert everything. If you don't want to allocate, then this iterator option might be very interesting for you. So either this one or any custom iterator that you define yourself, for example, using the Julia iteration protocol. So just defining this base iterate method on your structure, you get an iterator, and then you can generate edges out of it. All right, I think this is it for the SimpleGraph notebooks. If you have some questions on this specifically, are there some questions around?
Yeah, I've been moderating them pretty hard in the Q&A.
Okay.
Some that are left is people want to ask about distributed memory parallelism and GPU parallelism, or
Okay.
XLA for LightGraphs on tensor TPUs.
Okay, you might be more qualified than me to answer on this. Well, I know that.
I'll see. I want you to take a crack at it. And
yeah. Okay. So what we showed here is, again, the basic graph types. So the two basic graph types, which are SimpleGraph and SimpleDiagraph, and these are meant to start small and be good enough and scale well also. if you have some application where you know that you're going to have a lot of GPU operations, so for example, if you're doing a lot of linear algebra on the adjacency matrix of your graph, then it might be interesting to have a custom type that returns the adjacency matrix as a GPU matrix, for example. And this is exactly what we're going to see in the 7th notebook here. So we won't see GPU applications directly, but you will see how to define your own graph type. And this is fairly easy and a fairly small interface to implement. And so if you have this, this graph interface and you have some specific knowledge on the operations you want to do on it, then defining your graph is just a matter of a small Julia package, and that's it. And from this, then you can get the performance you want on the operations you want. So including GPU operations.
Yeah, now that the cool thing about defining a custom graph type is that you can automatically get all of the graph theoretic computations.
Mm-hmm.
If you do that if you store your graph as a GPU array, like a CSR matrix stored on a GPU,
mm-hmm.
if you call like what's a good example of something? You call like max flow on you try to do a max flow on your graph, it's gonna like take the data from the GPU, put it on the CPU, and do the computation on the CPU, which is kind of the exact opposite of what you're trying to do. So you would need to write a like custom implementation of lots of algorithms, and that's where multiple dispatch comes in, and why we love Julia so much for doing these kind of mathematical type of software. Is you can pick anywhere in the API to overload and say, okay, for my graph type, I have a closed form formula for this thing, or I have a faster algorithm that relies on the fact that I know my graph is a lattice, or I have a GPU implementation of PageRank, or something like that. So that's why we love Julia.
Can you guys hear me?
Yeah,
yep.
Simon, go ahead.
Okay. No, I just wanted to add something about the GPU graphs. There are some research projects, not in Julia, but languages for doing graphs on the CPU. The main problem with graphs is that usually they're highly irregular. They're not like, I don't know if you do like some grid problems where you have like U4 diagonals, then it's really easy to parallelize this on the CPU. But usually on graphs, you have like these small nodes which don't many edges and vertices with a lot of incoming edges. And then it's really hard to distribute this. And so I think this is also the reason why CPU algorithms have not caught on graphs.
Yeah, I would say that exactly that GPU algorithms and distributed memory algorithms for graphs too. Somebody else asked about distributed memory. You get the same problem at different scales when you go to GPUs are good at these highly regular problems. Distributed memory architectures are good at highly regular problems, just 3 orders of magnitude bigger in scale, but the same concerns about like memory traffic and network traffic are present. But yeah, so both distributed memory algorithms for graphs and GPU algorithms for graphs are open research questions, and I don't think there's been in another couple of years, maybe the research community will figure it out, and that'll trickle down or diffuse. I'll use a better metaphor. That'll diffuse into the software ecosystem, and we'll have good software for it.
I'll answer a question on the set versus vector of int. So the question was, does that still matter when your graph becomes large? Is it really still relevant? And it will become relevant because you will be creating a set for each of your vertices. So you will be allocating this much memory for each of your vertices. So it ends up mattering a lot. What it will scale with is with a number with the density of a graph. So if you have a denser and denser graph, then it won't matter that much more memory-wise. But usually graphs are sparse. Most applications get sparse graphs. So this would end up slowing down the creation of a graph and creating a graph very heavy. And the other question related to the notebook specifically was why instantiating SimpleGraph is faster than a dictionary. So this comes down to the underlying structures defined in Julia itself. So I will definitely say something stupid here. But creating a vector is fairly easy, fairly fast. And creating a dictionary, which is a hashing structure, is fairly heavy. You need to pre-allocate a complete vector with buckets and hashing system. So this will definitely be more overhead initially. And I think the other, so this one we answered live. Can you create a graph with an unspecified number of vertices? So I'm not even sure what the graph would look like. You can create a graph with a random number of vertices. You can create a graph with 0 vertices, but an unspecified, that would be a bit odd. So you can create it with 0 edges, which would make more sense. But a graph with an undefined, I guess you would just call a simple graph with random, and then you get a random number of vertices with empty, with no edges.
I think the other interpretation would be where your vertex set is the set of natural numbers. And so you just, if you say add edge between 1 billion and 1 billion and 1, like those vertices already exist because all natural numbers exist.
Yeah, I think you could create a custom graph for this, but some algorithms will definitely break, I think.
Yeah, and you would really, all the algorithms, they really need to think about like, well, what is the maximum vertex that has an edge?
Mm-hmm.
That's the thing that's what that number of vertices really means.
Yeah. And a last one, maybe before switching to the next notebook, I'll answer Tom's question afterwards in the answers. But how is performance of inserting and deleting vertices and edges? So these simple graphs are meant to have good performance also for deleting vertices and edges. So if you look at the adjacency list as it's defined, removing a vertex is just removing one of the entries in a vector, and then removing the corresponding entry in individual vectors which are sorted. And the fact that the inner vectors are sorted helps a lot to know what to delete. Mm-hmm. So yeah, that's designed to be fairly efficient to remove edges and remove vertices also, which would not be the case for other graph types.
Right. So often it's a good thing to like use simple graphs to construct your graph in an imperative way of like adding vertices, adding edges, using for loops to do that. You construct your graph as a simple graph, and then you kind of freeze it into another graph type that doesn't allow you to change it. Something like the adjacency matrix, right? It's harder to update a sparse adjacency matrix.
Right. So I'll answer the last questions in the chat directly, or well, in the Q&A. Simon, I'll let you start with the graph types.
All right, thank you. So let's see if I can share my screen. Does that work for you?
Yeah, I see. I see I3 as a window manager.
Okay. Do you see this Jupyter notebook now?
Yeah.
Yes.
All right, then let's get started. So for those people who are following along and also want to execute the code, I think they should just execute this first cell already because it loads a lot of different packages. And then we're going to do something magical. We call it creating this function with. It's not important that you understand what it does. You might go back later after you saw the chapter how the plotting works, but this is just something that makes it a bit easier for me to visualize the graphs I want to show.
So somebody asked in the chat, can you maybe put the window in full screen, like F11, I guess, and zoom in a bit? Yeah.
Is it full screen now?
Yeah, and yeah, perfect. Thanks.
Good. Yeah, and for those people who are doing work with a terminal instead of Jupyter, it's just important that you go down to this code and replace this gplot with gplot.html. Otherwise, you just get some random text on your terminal. Yeah, so let's execute that. And then let's start it with motivation for the random graphs. So let's create some small graph. we have this function called small graph, and it has some predefined graphs that we can create. Let's execute that, and yeah, so we get a graph with 5 edges and 5 vertices and 6 edges. It's not clear what it actually is, so we can actually look at the edges. It's still not clear what it is because we just deal with the edges. So we have now this function with, which just visualize this for us. Actually, now it takes some time. It's the first time to plot problem. All right, so it's called a house graph, and you see why it's called a house graph, right? So we are now going to look at something called the minimum spanning tree. So basically what it means, if you have a graph, you want to have a subset of these edges here that build a tree, so the whole thing is connected, but you want to have it minimal, so it must be a tree. So for this, in LightGraphs, we have this function called prim minimal spanning tree. Let's execute that, and it gives a list of edges. And now we can use this with function to actually plot this. So see, I have near that this color edges attribute that actually shows us here what is the minimal spanning tree. Let's go further and now do a bit of a different problem. Now we say, okay, we have some weights on these edges. And look, how can we build this minimal spanning tree so that we minimize the total sum? Yeah. So first approach is we're just going to store the weights in a matrix where you can the ij element of the matrix is basically the weight of the edges between I and j. For some reason, it has to be a symmetrical matrix because we're also working with an indirect graph. So let's create this matrix. Okay, there's a. So basically have now this matrix. So basically see, I put for every edge that is not in here, there's a 0. For every edge that's in here is a 1. But for the edge from 3 to 1, this is this edge here, we put 100. And we also can use our with function to actually visualize this. So you nicely see this here. So now this prim algorithm, it actually accepts this weight matrix. So we can put it in here, and you see, if we now visualize it, it has now selected a different spanning tree because it tries to minimize the total sum. So it tries to avoid this edge. So because this is a workshop, I'm trying now to do a bit of exercises for those people who follow along with the Jupyter notebooks. So I have inserted some exercises in this notebook, and I will give you some time, maybe 1-2 minutes, to actually solve this in the meantime. So what you want to do, we simply change this algorithm, this weight matrix actually. So that this minimal spanning tree consists of the edges 1, 3, 2, 4, 3, 4, and 4, 5. So if you look here, we want to have this edge, this edge, this edge, and this edge. Okay, so I will give you now a bit of time, and then I will scroll down and show you the solution for that. Maybe in the meantime, from Mattia or James, is something unclear in the chat?
I don't think we have questions for now on this one.
All right. So the problem is here, because now it's an online workshop, it's a bit difficult for me to estimate how people are proceeding along. So I just try to guess how much you will take for that.
Yeah, someone had a question. Is there value checking on the weight matrix to make sure that the weights are symmetric?
I don't know, but let's try it out. So we change now this matrix here. You see there's an incorrect value here. So let's run this prim algorithm where it is. Oh. I don't think there's a weight checking. There are some cases where we check if a matrix is symmetric, but not in all cases. And now something weird is happening to my keyboard.
Yeah, the LightGraphs philosophy of like checking takes time. We assume the user is going to give us good input. We kind of only check. We only check when the check is fast, or it's like hard to give, or it's like super important.
I think when we construct a matrix from a graph from a matrix, in that case, actually we check.
Yeah.
So I don't know, something weird is happening here, so I have to fix it first. Okay, no, actually we can go down now. So basically, you see, when we select these 4 edges, this means basically we just have to exclude this edge from 1 to 2 and the one from 3 to 5. So the easiest way to make a prohibitively high weight on these edges. So let's scroll down. So that's actually kind of what we do. We create this weight matrix and we set these edges to a high value, and then we execute this, and here is the solution. So now the reason why I did this motivation is now you want to ask yourself, okay, but these weights, maybe they belong to this matrix. So can we actually store the weights actually to belong to the graph? So can we store these weights together with the graph? And of course, there's an answer, and there is this package called SimpleWeightedGraphs that does exactly this. So analog to the simple graph and simple dgraph, and the SimpleWeightedGraph has 2 types, one for the undirected and one for the directed. And basically, what these graphs are, they're just a wrapper around one of these sparse matrices. So basically, adjacency matrices. But the good thing is, most of the LightGraph functions actually work without any problem if we use the SimpleWeightedGraphs there. So let's make an example. Importing this package, and I create a simple weighted graph from a simple graph. Basically, I just can pass this simple graph to the SimpleWeightedGraph constructor. Let's look at this, and you see the type is a bit different. We get a simple undirected graph with int 64 vertices, but also we have now this additional weights and value, and we can visualize this. And that's how it looks. Basically, because we did not specify any weights, it just used the basic default value of 1 and assigned it to each edge. We can also use that adjacency matrix here. So here is a matrix. You see it's symmetric. Yep. So you can imagine if I execute this now, then we get this matrix with 3 vertices. And you see it has the correct value. So from 1 to 2, it should be a 4. And this is the case. And it's also for the other edges. Yeah. Now, I can actually show you that the prim minimal spanning tree actually works, because it actually now selected the edges which not this edge with the high weight. So this automatically assumes that this matrix has some weights. Let's continue. What else can we do? Let's say we want to change the weight of the edge 2 and 3. This is a bit unintuitive because we already have an edge here, but we can just use this add edge function and pass the additional weight here. So let's try that. And voila, here we have this weight. And now here's a bit of a special case. Assume now I want to assign the weight 0. Then actually nothing happens, we get a warning. This is because it's a wraparound a matrix, and a 0 in this matrix represents no edge. So it's not possible to have a 0 weight. On the other hand, it's perfectly normal to remove an edge instead of zeroing it. So let's do that. And yes, we get this edge removed. Yeah, and if you now look at the adjacency matrix of this directed weighted graph, then you see that the adjacency matrix, instead of 1 and 0s, it actually has the weights. Yeah. So this brings me already to my second exercise. Basically, what I have here is a so-called directed star graph. You see, we have four vertices, and we have from the middle vertex, we have edges to all the outer vertices. So your task here now is, you should create a matrix that would represent this adjacency matrix of this graph, and ensure that the edge from 1 to 2 has the weight 2, from 1 to 3 has the weight 3, and from 1 to 4 has the weight 4. And then just pass this to the simple weighted dgraph constructor and see if it actually produces the correct graph. All right, then let's start.
In the meantime, maybe there's a question. Wondering if inserting, deleting vertices and edges is not as fast for weighted graphs as they are for let's say SimpleGraph and SimpleDiagraph.
Adding, deleting edges is slower than in SimpleGraphs, and the reason is that this wrapped matrix, the sparse matrix CSC, it internally is represented, I think, with 3 arrays. So instead of having a lot of different arrays for the adjacency list, you have some really big arrays. So if you make a change in the middle of these arrays, then you have to move around much more vertices. So actually, I think the best thing, if you want to create a simple weighted graph iteratively, is maybe to first create a matrix, or first create a simple graph, then pass it to this constructor, and then add the weights.
Also, another question, wondering if we make a matrix for weights, do we have to make the same values between Aij and Aj? So for directed, no, but for undirected, I'm not sure if it's an error that comes.
Actually, I'm also not sure, so let's try it out.
Yeah.
And let's make an unsymmetric matrix, 1, 0, 2, 0. Should work right. So it is an error. So actually, we do some checking there. Okay, I think time is up. Let's see what we do. Let's go to solution. So here is our matrix for this graph. Something that is maybe weird, that for this sparse for this matrix, we actually have the ones, the source is the number of the column and not the row, how somebody maybe usually would assume. And we just put in these weights here, and then we just thread and visualize it. And so easy it is, and they actually asked the correct weights. So I hope other people also got this. Yeah. So now when you're talking about this, you are talking, is there a way to have more than, you have different values on the edge? Maybe you want to have like a label, and you also want to have a weight on it. And yes, it's possible with another package, and this is called MetaGraphs.jl. Similar to the weighted graphs, it has two types, one for the directed and one undirected. And it is a wrap around the simple weighted graphs. And it internally uses dictionaries for properties. So let's see some example. I'm importing this package. And similar as for the weighted graphs, I can use this constructor. Here I use something called a ball graph, and then I visualize it. Yeah. So here, this is my meta graph. Now, something that is maybe surprising you when you saw what you saw before, there are no weights on this graph at this moment, because it doesn't assume some default weights. So let's see what you can do now. So to actually assign a weight to some edge, you use this setProp function where you pass in the graph, and you pass the start and end vertex, and you pass what kind of property you want to put, and of course the value. So you see already here, we put one value on this edge 1, 2. We put actually two different properties, one for this A and one for the C. And you also see this on other edges. So let's execute this and see what you get here. So you see this edge has the C, just the C property. This has an A and a C, and this is an A, a B, and a C actually. And in contrast to the simple weighted graphs, you can also use strings here. You can basically put any type as a property. So maybe you have this graph, you want to know what property do we have on this edge. You can of course do that. This is this get property function. It takes the edge and it takes what kind of property you want. Or you can also retrieve all the properties. Let's try it out. Yeah, for the first two properties, the single properties, so we just get this 5 and this hello, which is actually here. But for the second one, because there's an unknown number of properties, we actually get a dictionary that maps each symbol to each to the value. So, but this is not all that the metagraphs can do. We can also put on properties on the vertices. So let's see that. So let's say we have this metagraph. We have this vertex 5, and we want to put a name, and we call it vertex 5. So let's do that, and let's see what we get. And you see, it's maybe a bit difficult to distinguish, but on this vertex, you have now this property name, vertex 5. And you can even set properties on the graph itself. I don't have a way to visualize it, but here I will set the graph name to this bull graph, and then I will retrieve this name again, and let's see what we get. And we get bull graph. Yeah. So let's try to run our minimum spanning tree again here. And this is a bit surprising. It actually works. But now you maybe start asking yourself, okay, but here we have two values. And how can it be that we have, which value does it actually take for calculating this spanning tree? And to do that, we can use this function called weights in LightGraphs. And this is the function that all the other functions that take some matrix use internally to actually figure out what are the weights of this graph. So let's do that. We get the weight and we convert it to a matrix to actually see what's happening. And you see all the weights, they're actually ones. So all these properties, they were ignored. And this is because this metagraph, it has a pre-assigned field that is used for the weights. And we can figure out which weight it is, which property this is. And yeah, it's called something called weight. But we never assigned any weight to this graph. Never assigned to any edge some weight property. So of course we get this nonsensical value. So what we can do, we can actually change the weight field, the one it uses, and we say, okay, now you use the A. And we do that, and we visualize it. And then, of course, it uses the A field for building the spanning tree. Where there's no A, it just assumes 1. But this edge has A equals to 10, so it's prohibitively high, so it is getting ignored. Yeah. And this brings us to our third exercise, if you were following along. You see here, we also have this weight field called C. So what I want you to do is actually change the weight field to C. And before you visualize this, I want you to imagine or try to figure out what could actually be resulting spanning tree B, and then we see if it's actually the case. So let's get started. Any questions in the meantime?
Yeah, there was one on visualizations, but maybe we can keep it for the next notebook. It's up to you.
Okay, you decide. I don't know the question.
Well, can we plot edges to have a length representing the weight size?
I don't think we can do that. You also have a bit to think about the triangle inequality. I mean, at one point, it's not possible. You can assign weights in that way that it's not possible to actually plot this. It's actually, if you would say here, the length A is A would be the length of the edge, then you cannot plot this triangle because here it's 1 and here it's 5. So this distance is 6 and this is less than 10. So this will not be possible. But maybe there are some graph layouts that actually try to do some heuristics and try to actually, I don't know, put more force between this edge with a high weight and try to pull it apart. I am not aware of any of these. So
yeah,
time is over.
If you did the spring force layout, but you scaled the strength of the spring inversely to the weight, then you could get an approximation of what they're trying to get.
Yeah,
I don't know if weighted spring force layout is implemented in GraphPlot.
And I think there's also a big field in mathematics, computer science that goes about embeddings and things. I'm not so familiar with that, but I think this could be in a direction that of this embedding a graph such that this constraint are respected.
Yeah, so, I think the Jordan Lindenstrauss lemma tells you that there is a dimension at which you can embed the graph. For every graph, there is a dimension less than NV such that there's an embedding of the vertices into that Euclidean space such that the distances are preserved.
To be honest, I try to embed my graphs in less than 5 dimensions usually.
Yeah, right.
Okay, let's try to visualize this. Okay, let's look at the first. So we see here this C is really low on this edge. This C is also really low. Here it's 1. So just assuming this edge should be excluded properly. Let's try it out. And that's the case. Good. So after this MetaGraphs, now you might ask, when should I use which graph? And I want to start with benchmark. So we load this kind of big graph here with 30,000 vertices and 180,000 edges. So it's not that big, but it's still has some kind of weight. And from this graph, we build a simple weighted graph and we build a metagraph. Let's do that. And now, because we don't want to use the default weight in metagraph because this would be 1, so there's nothing in the dictionary. So we actually want to put something there. We assign to each edge the weight 2. And we also extract adjacency matrix. Yeah. And now we run this minimal spanning tree. We benchmark it 3 times. First, we use the simple graph with an additional matrix. Second time, we use this simple weighted graph. And the third time, we use this metagraph. So let's start with the first one. Of course, this takes now much longer than it did today. So 28 seconds. Let's try the weighted graph. I think the lesson is don't run Zoom while you're doing benchmarking. It also introduces a lot of noise in the whole thing.
Yeah, I'm getting cold sweats for the last notebooks also.
Yeah, so actually these are kind of similarishly. So let's try the last one and hide the conclusion.
To answer the question of should you escape G and A in the benchmark time, should you use like at B time prim MST $G, comma $A?
I think here it's not so important because the benchmark takes quite a while. But if you do this like really small benchmark where the calculation takes really a short time, especially in the terminal where the type is undetermined, then yes, you should escape it. Just for fun, let's escape something here. And let's see. So before it was 23, I think here. So we already look at the conclusion. So you see the metagraph, it takes like 10 times longer. And this is not so surprising because we're using a dictionary here. So maybe this answers your question. This is quite a bit faster actually if this escaped.
Well, given the Zoom noise, I'm not sure that 3 milliseconds is big. Given that on a quiet machine that might be a significant difference, but on a machine running Zoom, that's,
yeah. Okay, now it's like slower, so it's Zoom noise. But of course, I mean, you definitely see that the metagraph. This is not Zoom noise. This is clearly a significant difference to the autographs. So the conclusion is metagraphs are much slower. And when should you use which graph? So I would say the simple graphs, you use them when no edge property is needed, because why should you use another graph then? And this is very good because that we had the question before about the simple weighted graph changing. If you have to do a lot of structural changes, like adding, removing vertices, it's better to do this a simple graph than simple weighted graph. The simple weighted graph you can use if you have a numerical edge property, a single one. You don't need any vertex or graph properties, and there are not many structural changes. And the metagraph you just need when you need more properties. If they're not numerical, like if you want to put a string to an edge, you cannot do this with a simple weighted graph. And it actually should also be quite fast, or maybe a bit faster than simple weighted graphs for structural changes, because internally it wraps a simple graph and not these long arrays. Yeah. So let's see. We have some other graph types in the Julia graph system that I quickly want to mention. We have the static graphs. These are just simple graphs with a bit more cache optimal layout. Basically, everything is 2 big arrays. This makes it maybe a bit more cache optimal. I'm not sure if it were the price because they're basically mutable. So you have to put your graph already in there. You cannot change it. We have the special graphs. They're currently not in the Julia, how is it, general repo. So I did not include them, but there's a link here. This is something very interesting because if you have, for example, a complete graph, you don't actually need to store all the edges. You just need the number of vertices. Then you know what its graph is. So that's actually what we do. We have some specialized graph types there. Yeah, and it's pretty cool there because then we can specialize certain algorithms. You can calculate the diameter of a complete graph. It's 1. You don't need to run any algorithm. You just store that. Or is it 2? I don't know. And lastly, I want to mention this LightGraphs Plus package. It was created by our student Abhinav for last term's GSOC. and it's something I don't want to explain here, but there is this thing called GraphPlot, which is basically like the basic linear algorithm that we have for matrices. It tries to do the same for graphs. And yeah, basically, I think at least I am not sure if there's will actually something come out of this. It's still heavily in research, but it might also be an answer to the question before, how can we do graphs on a GPU? And because this GraphPlot is basically some kind of algorithm thing that you do, this might be easy to translate to the CPU. Yeah, so go check it out. It's maybe not polished yet, so I think whenever we get time, we want to polish it more and then pull it into the Julia system so everybody can play around. So what did we see here today? We saw this simple weighted graphs for single numerical properties, and we saw this MetaGraphs for non-numeric properties. Yeah, and I mean, I think somebody once said there should be as many graph types as there's matrix types. And if you play around with Julia a bit, you see there are a lot of different matrix types for all kinds of special matrices. And there's also, I mean, this duality between matrices and graphs. So there's really a possibility to do a lot of different graph types for each kind of application. Yeah. So I think this concludes this notebook for now.
Yeah, so let's take a break. Do we think 5 minutes is sufficient? We should definitely take at least 5 minutes.
Yeah.
So we'll meet back at, let's just do 7, and we'll meet back at 11:40 Eastern, 7 minutes from now.
Oh, so should we continue?
Yeah, sure.
Cool. Then I think it's my turn again. Is this big enough? Sorry, before I did not see that my screen was actually very small. So is this one now the correct size?
I think it's good enough. Yeah, we can read it.
Yeah, because it's a bit weird, but on my screen it's actually full screen. So
oh,
I can even make it a bit bigger. I don't know.
That's definitely big enough.
Okay. Okay, so previously you saw me using this with function, which was a bit magical. So actually now I want to see how we do actually plotting in LightGraphs with this package called GraphPlot. So first we run the setup again, and this time should be a bit faster. So let's create a small graph. It's called a partition graph. 10 vertices, 15 edges. Very well known in graph theory because I think it's a counterexample to a lot of theorems. But now let's plot it. So for this, in this GraphPlot package, we have this function gplot that you actually saw before. And if you run it, you actually see here this graph. I have to mention for people that do this in the terminal, they probably want to use the gplot HTML function, otherwise they just get some text in the terminal. And this actually opens the graph in a new browser window. Yeah. Maybe a bit interesting, if we repeat it every few times, actually the graph, it kind of changes. It's always the same, but still it's a bit different configuration. So yeah, this is a bit uninformative. So if in the previous notebook, you saw much more information, like we had different colors on the edges, we had some numbers here. So let's see how we do that. And the way you do that in Julia, you go to the help function and see what kind of things you have there. And you see now this function gplot has a lot of different arguments. It has the graph to draw, it has the layout. We will come back to that later. And here it has a lot of different properties that you can set. And I will just go over a few with you. So first, we actually want to know what label these vertices have. So if you look at the vertex, this vertex function, it just extracts the vertices. Yeah, and we collect them, and we can see these are the vertices of graph. Nothing special here. But now we can add this node label, and we just put in these vertices. And now if you plot it, actually you get this kind of labels. Yeah. We can do the same with edges. Let's look at all the edges. And then you just pass an iterator with that somehow gives a name to the edge. So here it's edges. And actually it puts this really ugly edge label on each edge. Yeah. So let's go a bit further.
That's less than
sorry?
That's less than convenient.
Yeah. Yeah, but I mean, one can put some transformation in here, and I don't know, then it looks nicer. Yeah. Okay, now we want to put some color, and for this we have this colors.jl package, which is really nice. I'm using it, and the way you can create a named color is use this special form, this colorant, and you put the name. So let's create some color red. And if you do this in Jupyter, then actually that is really nice. Then you actually see this color here. It's even nicer. You can put an array of colors, and if you enter this, it will print the whole array. So this is really nice. So what you can do, we have this nodefill C attribute, and we just pass in this red color here. And what happens? Each vertex gets the red color, of course. But maybe you want to have some different colors for each vertex, and you can do that. Yeah. Now we do something interesting. We still plotted load node labels again, and this node fill C, it will now be an array, or I think a collection is actually enough. And for each vertex, we will put if it's even or odd. We index into these colors, these two colors here. So if it's even, it will take the first color, and if it's odd, the other color. So let's execute this, and voila, we get all the odd numbers have the gray blue color, and the other ones have the yellow color. Same basically goes for the edges. Yeah. So it's time for an exercise, and we're going to do something very well known. Look, very well known in graph theory, and it's called Zachary's Karate Club. So we also have stored this in LightGraphs, and you can use the small graph function to load it.
I want to hold up 1 second, interrupt. I see in the chat several people asking, is he sharing his screen? Can anyone see?
Yeah.
Yeah, I see your screen.
Me too, yeah.
I see the screen as well.
Okay.
Okay.
Okay, no. It looks fine, yeah.
Oh, we're getting DOSed on the, okay. Confirmed, many people looking at the chat, and there's...
Yeah, the majority seems to have the screen. All right.
Sorry for the others. I think you have to rely on YouTube later.
Yeah, are we live, Avik, on YouTube?
Yes, we are. We continue to be.
Okay, so if you are one of the people who cannot see the screen share, then go ahead and look at the live on YouTube. I do also see a black box in the top right corner of your screen. I think that's an artifact of, that's like the Zoom window or something.
Yeah, there's this thing that can move around, but I don't know.
Okay. Yeah, I think that's a window manager and Zoom interaction. Okay, so sorry for the interruption.
No worries. Okay, let's go back to Zachary's Karate Club graph. So basically, you have this graph with, I don't know, maybe 50 vertices, and each vertex represents one member of this karate club. And basically, Zachary, he observed this karate club, and what happened there was a dispute between the administrator of this club and some instructor. And now each of these edges between the vertices, it represents the outside of the club social interaction between these members. So this would mean these two vertices, they never speak if they're not in a club, but these, they speak together if they're outside of the club time. And basically what I think Zachary can show, and why this is also used to test clustering algorithms, that basically this kind of graph, it decomposes into two different clusters, which are more loyal to the administrator and the ones that are more loyal to the instructor. Yeah. So what we're going to do, or what you are going to do in the exercise, you are going to run a clustering algorithm on this graph. And then you will get some clusters, and you should try to assign to each vertex the color of this cluster. This is a bit more difficult, and we will use this label propagation from LightGraphs to find the clusters. So yeah, and I have some hints here. First, this label graph is a randomized algorithm and does not always produce the same number of clusters. So don't be surprised. There can be one cluster, it can be 3 clusters. Yeah, that's the way how randomized algorithms work. And something else that is really nice is how, if you want to have different colors, you can use this distinguishable colors function. And if you do it, you get 10 different colors. So yeah, I think that's a bit, I don't know if you can see everything here, but yeah, I will give you now a bit of time to solve this. And in the meantime, of course, I will answer questions.
So there was a question, can you use the colorant property of the metagraph? Can you set the colors in the fields of the metagraph? And then
okay, so you could put a colorant there, but you still have to do the mapping yourself for the GraphPlot. This is a bit of a downside of our GraphPlot packages. It's not so well maintained as it should. It basically only works with SimpleGraphs at the moment. And if you want to map properties to edges, to labels or vertices, you have to do the mapping yourself.
okay.
So maybe one more additional hint, it's always good to look at the documentation of this label propagation algorithm. So I think let's continue. Let's see what is the solution here. So yeah, let's go down. As I said before, let's look at documentation. So label propagation, it takes a graph G and if you read documentation, you see it returns two vectors. The first is the label assigned to each vertex, and the second one is just the convergence history. Of course, we're not interested now in the convergence history. So let's just have a simple example. Here we have this barbell graph, and it has 9 vertices. And let's see. So if you run this label propagation on this graph, you get a tuple, and the first one, it assigns the 4 first vertices as get label 1, and the second one get label 2, as maybe one would expect. And this is convergence history, and we're not interested in that.
Can you draw the
barbell graph?
I think people aren't necessarily familiar.
So that's why it's called a barbell. It's like the one for weightlifting. You have a complete graph here with 4 vertices and a complete graph here with 5 vertices. And of course, what this label propagation does, it finds here one cluster and here a second cluster, as one probably should expect.
Yeah, if you get this graph wrong, your clustering algorithm is broken.
It's not my clustering algorithm. Why did I get it wrong?
No, I'm saying if a clustering algorithm does not recover
yeah.
the barbells in the barbell graph, it is clearly an incorrect clustering algorithm.
Right, yeah. You see, there's what's one wrong execution. This is really not a stable algorithm, this label propagation. I don't get it anymore. Okay, so basically, as before, we load this small graph, we calculate the clusters, we ignore the convergence history, so we just get the labels. We build this palette. I use the number of vertices plus 1. The reason is just that the first vertex in this palette is black, and then we cannot see the number. So I just shift it by 1. And then I just map the colors from the label to in the palette. And then I put it here, the colors, and then I plot it, and what we get. And yes, it found 2 clusters. As I said, it's a randomized algorithm. If we execute it a second time, we get. Okay. Now if a few times, we get a bit of different outcome. So this might actually make you think, is this actually a good clustering algorithm, this label propagation? Yeah. So, so much for properties. Something that you also might have noticed if you execute this, all the vertices that change the positions. And this brings me to my second topic here for plotting. It's the layouts. So let's start here. We have this, we create something called a grid graph. And then we plot it, and you will see why it's called a grid graph. Because it's a grid of 4 times 5 vertices. The only weird thing is how does Julia or GraphPlots know where to put the vertices? If we execute a second time, it's even nicer. And the answer, it is a specific layout. So this gplot, it takes an argument layout. So we can put in something called a random layout, and let's see how it looks now. And even though it's the same graph, it's completely nonsense. Yeah. So what is this layout? This layout is basically, it's just, it maps the graph to a vector of x and y's, where to put it. We can see this, we can execute actually the random layout on the graph G and look at the type, and we then, second time, we just execute it and looks what it actually puts out. So we see the type is a tuple of 2 arrays, and here you actually see the arrays. The first one is the x's, second one is the y's. So maybe let's look at 2 of these algorithms that we have in our in GraphPlots. So the first time is called a spring layout, and it's basically, it comes from physics, and the way it works is that you imagine your graph as being some nodes. There's some physical objects, and between each nodes that have an edge between them, there's a spring. So basically, this means if you would put this in reality, the spring, they would contract to a certain length. You cannot push them too close together, but you cannot extend them too much. And the spring layout, it just simulates this in kind of an iterative way. It does some time steps, and until it thinks it converts, or all the times are used up. Let's see. Plots and string out. Actually, now you see it's the exact same layout. It looks good as before. And this is because the string out is just the basic layout that we have in GraphPlot. You can look at the documentation of the string layout. Here you see the exact physical formulas. And you see it has a max iter that says how many iterations do we run this thing. So let's try it out if we just run it one iteration. And you see it's not so nice anymore. If we run a 10 iteration, it looks much nicer. And if we run 100, then it is basically already something nice. Yeah, so basically this is one algorithm that is inspired by physics. There are other algorithms for graph layouts that are inspired by physics. Now let's look at something completely different and called spectral layout. And the spectral layout, it's basically, it works with a matrix that comes from this graph. It's not a adjacency matrix, it's something called the Laplacian matrix. I think James could explain you much more about this, but let's just know that we have it. And let's see what happens if we run this now. And you see, actually, the spectral light, it also creates a very nice looking graph. It's a bit weird with this larger distances here, but it's also a layout which I find very nice.
Yeah, boundary conditions. It's because the corners have fewer edges than the interior points.
Yep.
So if you made it a bigger grid, you'd see the trend is that the boundary would be. Yeah.
Oh,
I love eigenvalues, man. That's beautiful.
I think in my experience, this spectral light, it mostly works for regular graphs, but as soon as it gets a bit random, it starts getting weird though. Yeah. So here's a warning. Graph layouts, it's a very hard thing to do. This is an easy to plot graph, but let's say we do something like this. This is a random graph with 20 vertices, and each possible vertex edge is there with 50%. So we create this graph and we try to plot it. And you see, basically the string layout doesn't manage to actually put this into something nice. You can also use the spectral layout and hope it gets better. And it's, in my opinion, even worse. Yeah. So, yeah, and this is basically my warning. Sometimes it's just not possible to put your graphs in a nice way, especially if you want to have like a 4,000 vertices. This is a very hard task. And I mean, when you start digging into these graph topics, you try to, for example, minimize these edge crossings. But as soon as you do that, you start to getting into the NP-hard territory. Yeah.
Right. So there's actually a deep connection of why the Erdős-Rényi graph and the spectral layout are so bad. That the Erdős-Rényi graphs are they're non-separable. So all cuts are bad, and so the eigenvalue, all eigenvalues of the Laplacian are big, and there's a reason for, like, the fact that all the eigenvalues are big in these graphs, which make them good at spreading information quickly. That, like, there's lots of reasons in theoretical computer science why you want graphs with this condition. It also makes them worst case for the spectral layout. And that's a deep mathematical fact about graphs that renders to us as like, well, these drawings are bad. Well, they're bad for a reason.
Yeah.
Somebody asked in the chat, Simon, what layout would you recommend when you have bigger graphs? When you start to get a lot of vertices, how do you handle that? Which layout would render it the best?
I think you have to think where they come from, but I feel this physical layouts, they work quite well. Yeah. As at spectral light, it seems to work quite well if the graphs are very symmetric. I don't know what's the reason for that, but otherwise something like the spring, there's another layout inside GraphPlots.
Yeah, the symmetry of the spectral layout comes from the automorphism group of the graph. If you have lots of symmetry in your graph, then you have lots of symmetry in your eigenvectors, and so that is cool. I mean, that's why I love spectral graph theory, is that it's like geometry of the shapes comes out in like you have shapes, and where you're talking about structure and geometry, you discretize them into graphs. You have symmetry in the graphs, then you convert them into matrices like the Laplacian matrix, and the eigenvalues and eigenvectors of the Laplacian matrix tell you about the geometry of the shape you started with. And that's a beautiful thing.
Mm-hmm. Yeah, just for the question before, I really don't know what you do with big graphs. You sometimes see this, people like trying to plot these really big graphs, and then it looks like there is kind of a connection there, but I think most of the time it's just noise and it looks nice, but there's...
Seth always says, if you
don't see more information,
graph, you've already lost. If your problem-solving technique involves visualizing the graph, and the graph has more than 1,000 vertices or something, you're not actually solving the problem, which is to compute the answer to your problem from the graph. So visualizing is very important for like debugging algorithms and for putting images in papers and doing toy examples and illustrating and teaching, but it's not useful for an actual problem-solving technique where I'm going to take the power grid of a national scale power grid and I'm going to visualize it, and then I'm going to be like, cool, now I know everything I need to know about the power grid. No.
Yeah, actually, I think if you visualize the power grid, you at least get roughly the map of the country back.
Yeah, it's like these maps of any the number of people who have X. But that's basically just a population density map of the country that you're studying. So
anyway, yeah, I have also another small exercise for you, and I want you to plot a wheel graph. I will just show you first what is a wheel graph. Wheel graph is basically a graph with a single vertex inside and like a circle around, and each of these vertices outside is connected with a spike-like edge to the middle pivot. For that, we actually have this wheel graph function in LightGraphs that creates this kind of graphs. And basically, what I want to do is create this wheel graph, try to plot it with spring layout, and try to plot it with the spectral layout. And then I want you to also try to create your own layout that puts the vertex in the middle here, and everything lies around nice in a circle. And also try out this with, I would say, 100 vertices. Don't try 200, this might fail, but 100 vertices, and you will see that not everything works as well as before. There's some hints here. The vertex 1 is always in the middle. Scale does not matter if it's not in the right scale. Like GraphPlot will just scale it to square. And for your basic geometry, if you have the k point on an endpoint cycle, you can use this very convenient formula. And as you saw before, a layout is just a function that maps a graph G to a tuple of vectors, x1 to xn, and same for you. Yeah, so let's go. And of course, as always, in the meantime, I can answer some questions if there are any.
Yeah, there was one question I hadn't answered from Steve. And it's basically, where is the small graph function from?
The small graph function is built into LightGraphs.
Okay.
No, that doesn't work. Scroll up. I hope it's okay for everybody over here. So you can look into the small graph. No, it doesn't. Oh, that works. And yeah, it has some kind of built-in graph types.
Mhm.
It's really easy if you want to have a small graph for quickly doing something.
Right. It's also a debugging and pedagogical tool, right?
Yeah.
I find someone asks, how do you save these SVGs out into files?
For that, you have to go. Let's look at the output type of this gplot. So the output type is actually something called compose context, and this means it comes from a package called compose.jl. And what happens here, if you just get this type, then Jupyter knows how to draw it, so it just plots it here. Otherwise, I think you have to go to look into compose.jl, and there should be a function to store these SVGs. I'm actually not sure if GraphPlot has something built in.
I found it in the docs, and I can post the answer. So using compose and then draw. You have to make a window. You have to make a PDF or PNG or SVG file, and then you tell gplot to plot to it, and then you save that object. The compose manual is the ultimate authority.
Maybe I'm always a bit confused with compose, I have to admit.
Yeah, the taking screenshots from the Jupyter Notebook approach is the quick and dirty way.
All right, click on it. Good. Yeah. So let's slowly continue. Solution. So first, we want to try with a bigger wheel graph with 100 vertices, and we just tried out with the spring layout. So let's look what happened. And you see, this looks nice, but I think it's not what you really want. It just kind of shows us here how the spring layout fails. So then let's do the same with the spectral layout. And this is very nice. The spectral layout really recovered the structure here. And now let's try to write our own layout. So our wheel layout, it takes the graph G. And this n is the number of vertices on the outer wheel. So it's 1 minus the vertices of G. And then it just basically creates these 2 points of x and y's. It puts 0 here for the first point, because this will be the coordinate of the middle spike. And then we just map from the index 1 to n to the points in the circle with this cosinus and sine formula. And if we execute this, you basically get the same as in the wheel layout graph. So let's summarize. We have seen how we can plot graphs with graph plots. We have seen how we can put some attributes there. And we have seen how this different layout works. Now there's something I have to say. This GraphPlot package, it's not in the best shape at the moment. I think somebody already asked in the chat about some pull request of his that is not being taken care of. Yeah. So it's I think it's really something we have to put more time into, but plotting is hard and time is limited. Then I should mention there's another package called Graph500.jl. It's not in the JuliaGraphs ecosystem, so I don't know much about it. But for me, it looks a bit more polished. And I think at the moment it's a bit slower than our GraphPlots because just internally it converts to a full matrix. But this should be easy fixable. Somebody will just do it. And if you really need to have good plots, then you should probably use a specialized software for graph plotting. Graph500 is a well-known open source software. You just export your graph and then you put it in there. And there's a lot of research in this software and it will put your graph into a nice shape. Yeah. That being said, I mean, GraphPlot is still kind of easy to use and could be used in the future, for example, if you want to research new graph layout algorithms. So basically, this concludes my part for now. And
great. Yeah, I'd agree that the graph plotting ecosystem needs a little love and
polishing.
And yeah, as open source software works, you know, software gets written if it helps people do their, you know, achieve their goals. So if you have a reason where you need more sophisticated graph plotting and that's an area that where you have an interest in contributing, that's a great area. All of LightGraphs is open to contributors and we're very, I think we do a pretty good job of welcoming new developers into the community and at least I try to, so I hope we're doing a good job. Yeah. I mean, I know everyone tries to, so I think we're doing a good job. Great, so let's move on to the next topic. I think Matthew, you're...
Maybe do we answer maybe the last questions on visualizations? Is the spring layout akin to Früchtemann-Reingold?
I know about Früchtemann. I don't think that's a different one. Maybe we have it in GraphPlots. Don't. It's been a while since I looked into it, so I don't remember if it's the same. I don't think so.
Per Wikipedia, it is a type of spring directed layout. So
all right, it is.
So it's related. Oh,
actually, yeah. If you look at documentation, it says Früchtemann-Reingold. Okay, so it totally is.
So it's very related.
Some other question?
So is there a relationship between dimensionality reduction and graph layouts? So James, do you want to talk about categories or?
Yeah, so dimensionality and graph layout. Graph layout is dimensionality reduction. You can think of the either dimensionality, like thinking of the rows of the adjacency matrix as samples from a stochastic process, and then graph layout is the reduction of that to, we support two-dimensional layout. 2 and 3 would be the most common, and the spring layout is similar to something like multi-dimensional scaling, which is a statistical technique that for dimensionality reduction. And it is also based on this, like you have some functional that represents the energy of your data, and you want to minimize that functional based on like data that's close in the high dimensional space needs to be close in the low dimensional space. So definitely, graph layout is dimensionality reduction from the number of vertices is the high dimension down to 2, the low dimension, and you're reducing to, for sure.
And the last one will be specializing. Do we have a way to dispatch on some graph types in GraphPlot? As to specialize a given layout for a given graph type.
No, we don't have at the moment. It's really just use the LightGraphs interface.
Okay.
Yeah, that would be a good. That's a good thing to do. You can do that in your own package. So if you define a layout for your graph type, you can import the gplot function and add an additional multiple dispatch. Another method to that function that will default to your layout that you write. So great. Yeah, another case where like being open in the sense that Julia functions are open to accepting new methods on them allows you to extend functionality, kind of that compositionality of the Julia ecosystem, which is great.
Okay, I think then we should continue, I guess.
Yes.
So who's next?
Matthew, you're up. You're also on mute.
Yeah, might be better without it. All right. So, so after seeing the key tools and the center of a toolkit of LightGraph, we will see a bit some applications. I hope this is big enough here. Let's remove view, single document like that. Sidebar. All right. So is it big enough for everyone?
Yes.
Okay, perfect. So so we'll see two notebooks for applications of LightGraps to see a bit more hands-on things. Not now that you grasped, I hope, the center of how you would use it. And the first type of applications will be optimization on graphs. And so by optimization, we mean taking a decision that's the best one possible given some constraints. And optimization on graph will be deciding something on your vertices and something on your edges in some very generic way. So for that, I will first import the packages you've seen several times now, but also jump and some solvers that go with it. So we'll see exactly what these are. So optimization on graph. So that would be usually, for example, find a subset of the vertices or a subset of the edges, or assign some quantities to the vertices and edges. And so assign these quantities such that you maximize or minimize a function. And you have, your quantities being either binary or continuous on each of the vertices or edges. Right. So, wait, let me just get something. Yeah, jump. So yeah, moving on to jump. Jump is an ecosystem and a package in Julia for constraint structured optimization. So it's defining a domain-specific language, DSL, for solving constraint optimization problems. So it's based on macros, and so this is allowing you to get a special syntax that is more familiar for people doing optimization, while being in standard Julia. So you can use these macros just like any other Julia code. So to give you a small example here, a small crash course. So this is here creating a model object in jump, and then these two macros will define two variables. So here, so we create this model M, then this variable X, which would be a vector of 3 variables, all have to be positive. And then we'll create a matrix of 3 by 3 binary variables here. Then we'll add a constraint. So we have this X and this Y defined. And now I will attach to my model a constraint called my constraint, and there will be 3 constraints from 1 to 3, and each of them will be X has to be smaller than 4 times the sum of yij for j in 1 frame. So this will be my constraint, and then the objective, so the thing I'm trying to maximize here would be the difference of the sum of x and the sum of y. And then I will just print my model here to see what it looks like. Yeah, again, this is usually not too slow, but I think my laptop might be suffering a bit from Zoom. Right. So here, jump models render fairly well in notebooks using some LaTeX style. So what we have here is the expanded model, so the sum of x minus the sum of y, and you're trying to maximize this. Subject to, so these are my 3 constraints and my variables there. All right, so that was just to show you how you use it. And then once you define your model, so JUMP is only for defining models. It's a modeling toolkit. It's not a solving toolkit. So once you have your model defined, you can pass it to a specialized solver, which uses some algorithms depending on the type of problem you have. And so here, one example would be this CBC solver, which is open source, and which we will use to optimize our problem. So this will basically pass our generic JUMP model in a specialized form to this underlying solver, solve it, and fetch back the result into this model object. And so once we have this model optimized, so yeah, this line here is just to avoid having verbosity of the output of the log of the solver, and then we can fetch back the results of this y variable, which is in that case y. So this is here the optimal solution we found for this problem, so for the y variable, and we could do the same thing for the x variable here. Right. So that was it for the basics of JUMP. So now we'll get back to graphs. And the first thing is, so we'll try to solve some flow problems. Right, so we'll first create a simple diagraph here and add some edges. And then we'll define a capacity matrix, which would be non-symmetric. Since we have a directed graph, it's not a problem. And we'll just represent this flow problem here, just to see what it looks like. All right, so yeah, that's basically the graph I'll be working on. So it has some vertices from 1 to 6 and some edges, and I assign some capacities here. So a flow problem is basically making things circulate from vertices to other vertices, passing through the edges of your graph. And so this can be if you have a road network, this can be trucks or cars that you circulate between vertices or cities or anything. If you have let's say chemical systems, this could be components flowing through your plant. This could be really many things, well, many different things here. An important thing is if you solve a flow problem in a continuous manner and you have your problem well defined, you will get integer variables at the end, so integer solutions. And so here it means you won't have, if your capacities are all integers, you will not have your car split into between 2 edges. This will always be one car going through one of the edges and not the other. All right, so you have different variants, different flavors for this flow problem. The basic one we'll be using is called the max flow problem, which is basically, so I have, in my graph, I will have a source, here 1, and a sink, 6, and I will try to make as many units circulate from 1 to 6. And so this is a basic max flow. You have other variants, for example, the min cost flow, where you need to circulate at least some units. So for example, you need to make at least 2 units move from 1 to 6, and you have to do that at least cost, given that some edges might have some cost. Okay, so in that case, we're just not going to consider cost. We're just going to consider that we want to make some flow from the source to the sink, and so to maximize this amount of flow. And so in flow problems, you usually have at least 2 constraints, which are, so the edge capacity. So you have to have a positive flow on each of the edges. So, and it has to be between 0 and this capacity. So from 1 to 2, I can make some flow from 0 to 2. Okay. And the second one is flow conservation. So at each vertex, which is non-terminal, so except for the source and the sink, for all of the other vertices, the amount of flow in is equal to the amount of flow out. I cannot have accumulation or I can have destruction of flow at any of the other vertices. Okay. And so that's my only two constraints. So I can get that into a mathematical formulation of the model, which would be, for instance, what we have here. So I'm maximizing over this variable f here. And I need to maximize the flow from 1 to 6, so I can phrase it in different ways. One example here is I will maximize the amount of flow that goes into 6. And since we have flow conservation, this is equivalent to the quantity of flow that flows out of 1. So we'll maximize over the vertices I such that IT with T my sink is in the edges. So I will maximize over all the edges coming into the sink, the quantity of flow. And then for any vertex that's not the source or the sink, I need to have flow conservation. So on the left-hand side is all the flow going into my vertex V, and the right-hand side is all the flow going out of this vertex V. And then lastly, so my last constraint is my capacity here. So my flow can be between 0 and the maximum capacity of the edge. So you can think of capacity, if you have a road again, that would be the maximum traffic you can have on a given road. If you have a plant, that would be the maximum physical flow you have, or anything else. Right, so I will give you two versions of how to solve this problem. The first one will be using jump from scratch. So we'll just create a model, formulate our problem on our graph, and then solve it. And the second one will be using LightGraph flows. Right. So just like before, we'll create this model here, and then create this variable f, which would be a vector or variable indexed over the edges. So instead of being indexed over integers, this would be over edges here. And so each of these f is constrained between 0 and my capacity for the corresponding edge. So that's my first constraint. And then the second one is the conservation constraint here. Can you see the whole screen? Because I have faces on the side. So
Yes, we can see all the way to the margin.
okay, perfect. So here you have this second constraint, which is the flow conservation. So again, flow in equal flow out. And so here, this is the name of a constraint. And then I index it by the vertices. And I can filter here, so V for all the vertices of G, such that V is not in 1 and 6. So V is not the source or the sink. And then this is basically just summing up the incoming and the outgoing flow. And finally, maximizing my objective, which is maximizing the sum of the flows of E for E in the edges if the destination of E is my sink here. And I can visualize my problem, so we get here the same type of index as we had on GraphPlot before when we had the graph visualization notebook. So we have this flow from 4 to 6, from 5 to 6, and so on. So we're maximizing these two here, which is the sum of the flows going into 6, subject to that's here the 4 flow conservation constraints, and then the capacity and positivity constraints. And so we can set our optimizer to silent, optimize, and then fetch back the result, which will just be rounding to integer the value of the flow here. And then we can visualize the result, and the edge label will be here the resulting flow and the capacity. And so we see that almost all the edges are saturated except this one here. So we are flowing 2 here, which is then split 1 and 1. And then so we have 1 here and 2 here. So the real constraint is you can define different cuts. So the real constraints are the saturated edges. So 1, 3, 1, 2, and so on. So the only non-saturated one is this one here. All right. So the question is, how do you do if you know you have a flow problem, but you're not sure you want to use jump, or you find it too complicated, or you don't want to formulate the problem yourself because this can take a bit of training. Then you have a second option, which is using LightGraph flows, which is basically defining these max flow problems, min cost flow problems for you. So instead of having to go through the process of formulating this optimization model here, you can use LightGraph flows, and you just have to pass to this maximum flow function your graph, the source node and the target node, so the sink node, and then you pass the capacity matrix. And so what you get back is a tuple with first the maximum flow value. So how much flow did you manage to circulate between the source and the sink, and then the flow variable, which would be your matrix. So again, I can visualize my graph with the resulting flow. So instead of using the one from jump, I'm now using the one I computed from LightGraphs, and I get exactly the same result here, with the only edge non-saturating being the one from 5 to 6. All right, do we have some questions up to now?
I don't think so. I don't see any.
Okay. So I wanted to show you another typical example of optimization problem you have on graphs, which is the minimum spanning tree. So Simon showed it already, so you're now familiar with it. And the interesting part on that is that it's a hard problem to solve using the mathematical optimization techniques, so the mathematical formulation or using jump or anything like this. It's non-trivial to solve using that. While it's super simple to solve using some custom algorithms for it. So again, so you've seen that already. So I'm gonna go quickly over it. Basically, you can use the Kruskal or Prim algorithms for minimum spanning trees. And what it's doing is computing a subset of the edges such that you connect all the vertices together at some least cost. So if you don't provide the cost, it corresponds to finding the edges that connect all the vertices such that you minimize the number of edges you're taking. And so we saw that already, so I'm going to go quickly over it. You can also do that with some weights. So here I'm going to define some random weights and make it symmetric by adding weights to its transpose. And then rerunning a Kruskal algorithm, but now with weights, and we get this result here. So for some ideas of applications here, you can think of it as, well, I have some cities and I want to connect all of them in the cheapest way. For example, if I want to connect cities for electricity, for telecommunication networks, things like this, then how can I connect all of my cities such that all of them are connected to the same subset of edges in some least cost manner? And so this is fairly fast to solve. This Kruskal and Prim are both running in polynomial time. Right, so on some very vague guidelines of what we have in LightGraphs, we usually have more established problems and established solution methods as the reference ones, as opposed to things that are still ongoing research and that, well, it's still not clear which should be taken or integrated. We usually tend to get to take problems where we have some fast solutions. So because NP hard problems, again, have some specialized tricks and formulations to try to make it a bit faster. So we don't have that many of them, or do we have any of them at all? I'm not even sure. And usually we also integrate more exact methods or methods with at least some guarantee on the performance and on the quality of a solution, as opposed to heuristics, for example. All right, so that was it for the first application notebook. Do we have questions?
So one question was, what's the algorithm used for max flow?
So for max flow here, so the default one, I'm not even sure. So you have an algorithm that's not using the simplex linear optimization algorithm. You have something custom for max flow. It might be CARP, I think. So there's a default one, and then there's a bunch of others that you might use. And you can also define your own algorithm and just implement a new method and use it just like that. So one of the keyword arguments here for Maxflow, you can actually see it by, let's see if I can do that. So in a notebook or in the REPL, if you open parentheses like this, you tab and you get, I think, yeah, you get the different methods that you might use. And so you see what are my arguments, what can I put, what are the options I can use. And so I think in any case, you have the algorithm here, which is so push relabel or Kolmogorov or Dinic and so on. So you have different ones to choose from.
Great. Yeah, let's move on to the package ecosystem. And then I'm getting cognizant of time. We go for another 20 minutes or another hour. Okay, not an hour and 20 minutes. Okay.
Yeah. All right. Okay. So the other type of application was a bit more hands-on. It's more focused on the application itself than on the problem class. So it was trying to analyze the general registry of Julia. So I pulled the data recently. So if you want to rerun this notebook, you will need to clone this or download this somewhere, and then change the path here to have a good path to general. So you basically clone this repo here, which is storing all the registered packages in the general registry of Julia. So let's say it's the generic registry where you add your package when you think it's good enough for other people to use. And so what I'm doing here is just getting the path to where I cloned it, which is just one step above in this above my folder. And then I will parse the registry file, which is basically all the packages present in the repo. Fun fact here, if you want a tunnel package in Julia, the cheapest one available is already there in PKG. At some point, I think it should be moved out of it into an official package, but for now, you just have it right under your nose in the standard library. So yeah, so this registry file is basically composed of different entries, and the one we're interested in is this packages entry here. Which is storing for each UUID here, it's storing some information on the package. So here I'm going to get this package info, which is this packages entry here, and get started. So I will use the standard packages we've seen so far, so nothing fancy. And then I will map, so I will get my packages info and then just get back the name and the path because that's the only info I'm interested in. And then see what's the first package. So the first package I found here was Cosma.jl. So it's a binary builder package, which I guess are increasing in number these days. So yeah, I have basically for every package, I have its name and the path to get it in the general registry. Because, well, the paths are ordered by first letter / and then the package name. All right. So first, I'll define a function here, find direct packages, and we'll walk through it because it's a bit more dense. So it's taking an argument of the registry path and the packages path and a source package, and it will give me back the packages that depend on this source. So if I use LightGraph here, I will get back a vector of different packages that use LightGraph, that have LightGraph in their project toml file, or in the registry in the depth toml file in that case. So I basically go over the packages and then verify that it has a depth file, because some packages don't even have dependencies, and then they don't have this depth toml. So it has this depth file, and it has in the structure in the dependencies this source package here. Right, and so I can see who depends on LightGraph now. And we have 92 elements. So I pulled it out. I synchronized master today. So this is really fresh from the boat. Maybe we could see some other packages. Who depends on CatLab? Yeah, it might be still too soon for this. I'm not sure. Oh, already five. Okay, we have people depending on CatLab already. You could check. I guess lots of people depend on distributions because
It's a good thing that you pulled the latest Julia registry. Otherwise, that would have been a shorter list.
So yeah, one trick here is, so it's not measuring the importance of packages, because some of them will be end user packages that you would not import into your library, but that you will use yourself directly as an end user. So for example, one that's very biased for this is differential equation, which a ton of people use, but they lots of them use it for their research directly, so not to design packages, because, well, differential equations is also the umbrella package importing everything for you to have as a toolkit. So I think it has less elements here. So that's the one directly depending only on differential equations, why I think what you would import would be some base ODE, so a lighter package that's defining the methods. So yeah, I don't know. Do some people want to see their package? Do we have some?
I think for time we should.
Yeah. Oh yeah, right. So right. So now we know how to get the packages depending on something. What I want to do now is, from a given root package, so from LightGraph, for example, I want to see who depends on LightGraph, and then who depends on these packages transitively until you reach something that nobody depends on. And so you will build a sort of directed tree with this, starting from LightGraph and going down to node packages, to leaf packages, if you will. So here, this is basically calling this find direct depths iteratively until you don't find anything anymore. And so we can get this tree for LightGraps again, which will end up, I think, a bit more than 200 packages in total. And then so at each node, so we not only add the vertex, we also add the property name, which will be the name of the package. Otherwise, we just have numbers and we don't remember what 34 corresponds to. And so once I add all these packages, I can verify what are my outer neighbors of a vertex 1, which is LightGraph. And so I should be able to find the packages directly depending on LightGraph again. So my 92 packages, if all goes well. Yeah, again, don't take this time for granted. This is mostly my PC suffering on Zoom. Right, and all right. So we have this this graph with 230 nodes and one less edge, which makes sense because this is a tree. So all the vertices are connected to exactly one other vertices, except LightGraph itself, which doesn't point to anything. And we get back, so the direct the ones directly connected to LightGraph are again our direct dependencies. So we can wonder what's the height of this tree. So how far do we go from LightGraph to any other package depending on it? And for this, we can just call this shortest path function. And so we compute the shortest path from LightGraph to any node, and we end up with LightGraph being at distance 0 from node 1, which is itself, so it makes sense. And the maximum one would be this last package here, which is 6 steps away from LightGraph, which is this NTNK, which I'd never heard of before. Another thing you can compute is this number of packages at each distance from LightGraph. And so you end up with one package which is at 0, which is LightGraph itself, this last package 1, which is 6 steps away from LightGraph, and then all these others in between. And then again, we can play with wondering what are the packages that are 5 steps away from LightGraph, and then you get these ones, which are given here. So we computed a tree with these packages. But what we can also do is take the same packages and compute the full subgraph. So adding all the dependency links, which will not be only in a tree structure, but really whenever you're depending, you have a dependency from A to B, then you add an edge. And so for each of these vertices, I will just, so I have the same vertices as my tree graph, but now I will add all of these edges one by one.
So Matthew, I think we should move on to the next topic because we only have 10 minutes left.
Oh,
and,
yeah.
And that's a good stopping point.
Yeah, I think so, yeah.
Okay, so Simon, let's do the Graph.io topic for the next 5 minutes, and then we'll finish with the custom graph types. We've mentioned the grid a couple of times, so I want to hit that.
So everything working? Can you see my screen?
Yeah. Good.
Yeah, so now I want to quickly talk about importing, exporting graphs. Yeah, as usual, we run the setup. Yeah.
So basically, there's some ambiguity. I thought we only had 10 minutes left. Some other people are saying that we have an hour and 10 minutes left. Avik, can we get a?
Generally, we have scheduled these for 3 hours, so that is 10 minutes. But we can go over a little bit. Although I must say we have had a few people drop off, so
okay, yeah,
we still have about a few hundred people across the 2 platforms, so we could go a little over. It's fine.
Okay, we can talk. So yeah, let's plan on wrapping up and then respect everybody's time. Wrapping up in the next 10 minutes, and then we'll stay online and take questions, and so we can come back to things if necessary.
So I will just quickly summarize this Graph.io. So basically, there are different graph formats, and we have this Graph.io for package that basically allows us to load and save graphs. So you can look at this later, but we have this kind of 2 functions. There are various graph formats that we support. We don't support writing and reading for everything. Actually, we support that. It's just not merged to master yet, so it's not here. Yeah, so quick example here with the create a small diamond graph, and we write it to the GraphGML format. And actually, instead of writing to a file, we just print it to the console. Yeah, so basically you can see, but instead of std out, you could also route this to a file. And in that case, I will skip this exercise, which has just to export the graph. Yeah, importing graph, similar. So I didn't want to go over it anyway. So what I want to show you is if you need a lot of graph data, there are some very good graph websites. Please go check it out later. And one thing you actually seen before, we have this SNAPDatasets. It contains a few big graphs from the Snap graph collection. Yeah, it's pretty easy, simple to use. You can load different graphs you can load here. So then that's all from my side, and let's continue with James.
Okay, so I made the mistake of updating to the latest, and now my notebook is totally broken. I'm getting a bug here. So I don't know if I want to fix it or move on. It's just an inexact error in the plots, but it really does ruin it. Inexact error.
So quick note, James, we had scheduled this for 3.5 hours, so
okay, so we're planning
to go over for another 35 minutes.
Okay. maybe we should go back, and I will debug while we do that. So,
or we just do a Q&A session in the meantime.
yeah. So yeah, let's take questions on either the applications or the what we just talked about, I/O, which we whizzed through. So there probably are some questions, and I'll try to get this fixed real quick.
So, wasn't there?
I think people are wanting and want the live debugging. They want to see you struggle in front of your screen.
There was one person that once raised the hand. Should we allow them to talk now?
Sure, yeah.
So I hope this person is still here. So I press allow to talk, and Priya Sharma is free to talk now if he wants, or she. Or if somebody else has a question and want to talk, they can raise their hand now. Or just ask in the Q&A session, of course. So there is this question, I'm not sure I understand. Could you discuss how to solve the linear assignment problem using LightGraphs? Are you familiar with that?
I've seen it. I don't remember exactly which one it is, but I've seen it before. I think it's one you can't solve in polynomial time. It's one of the MILP type of problems. So I guess you would define it as I had for the flow problem from scratch with jump. And so you would take an input your graph and some weights. And from this on, you will create the jump model and create variables for the vertices and for the edges. So it's fairly compact, and you don't need to create matrices or anything like this. You really reason with variables being defined on over vertices or edges, so it's fairly easy for that. So it's not in LightGraph itself. It will be combining LightGraphs and jump, for example.
Mm-hmm. Yeah, there's somebody called Jorge that wants to talk, so I will press allow to talk now. Oh, but I cannot because he's using an older version of Zoom apparently. So
Oh.
you have to ask in the Q&A.
Okay. There's one question from Steve that I can take. In the package dependency, I'm getting a binding meta digraph does not exist. I think so. Either I forgot to put something, or normally you should run first the first cell or the second cell with using LightGraph, GraphPlot, using MetaGraphs, and the binding is in MetaGraphs itself.
I got the bug fixed.
Cool.
And live streamed on YouTube, me staring at the screen in a puzzled manner. And I'll point out the bug so we can laugh about it.
Perfect.
Okay. So do you see a Chrome tab with my notebook?
Yeah.
Perfect. Close this guy. Okay, so
maybe make it a bit broader if you can, or zooming in.
Settings. There's a presentation mode in Julia.
Yeah, in view. Yeah.
That's where it is. Yeah. Okay. Better?
Yep.
Perfect. Okay, so we're basically going to define two types of graph. One which is suppose you're actually trying to do dense linear algebra on your graphs, and so the appropriate data structure is the adjacency matrix. So that's the first thing we're going to do. And then the second is suppose you're doing physics problems and the integer lattice of a grid is the appropriate data structure. So we're going to go through both of those. So we have our imports, and then our matrix graph is going to be defined as taking a one field, M, which is going to be some abstract matrix of bools. And our constructor takes that matrix and stores it in that field.
It's 13 hours.
So then when if you pass a integer, we're also going to define this auxiliary constructor for making a matrix graph from an integer, which will make an n by n empty sparse matrix. Okay. So in order to define your custom graph type, you have to satisfy this interface. It's pretty minimal. It includes, so you have to articulate, is your graph directed or undirected? What is the edge type of your edges? The number of vertices, the number of edges, and what is the set of vertices? So we index that with base 1, 2, NV. Okay, so you can make a 4x4 sparse matrix of bools to ints. And then calculate, okay, what are the edges? So the edges of a matrix graph, you iterate for all rows, for all columns. There's an edge from I to j if there's an entry in ij of the matrix. You can define and I think this true and false is for directed or undirected, right? So then you can get the out neighbors is just for a specific row, right? So for row V, you sweep over J, and there's an out neighbor if there's an edge, or if there's a 1 in entry M of V comma J. For in neighbors, it's the same, but backwards. So you can see that this is not going to be efficient if you have a sparse graph, because in order to calculate, like, let's say every vertex had 4 neighbors, but there were a million vertices. The out neighbor function is going to be linear in the number of vertices, even if the number of neighbors is a constant. So this is the exact opposite of what you'd want to do if you're trying to store a large sparse matrix, or sorry, a large sparse graph. We can do mutation on our graph by just changing entries. So one of the great things about this approach is that adding and removing vertices is constant time. Sorry, adding and removing edges is constant time, because all possible edges have a slot in your matrix if you're using a dense matrix. So you just have to like index into this matrix and set it to true. Removing vertices is not feasible because it involves deleting rows and columns out of a matrix. So we're not going to support that. But removing edges is constant time because it's just setting a certain entry in you're just flipping a bit from true to false. So if you want to accelerate computations so once you've satisfied the interface, every function in LightGraphs will work for your graph type. It might not be efficient though. So the default implementation of the adjacency matrix function on this graph takes 26 milliseconds. But we could define a new version of adjacency matrix that just accesses our adjacency matrix here, which then takes 328 microseconds. And these are with Zoom running times, right? So it's slowed down on my poor laptop suffering under the burden of Zoom. Okay, so yeah, Huda Nassar has written matrix networks, which really takes this to the maximum. It's like, the lab that she did her research in for her PhD is driven by the view that like graphs are just matrices that happen to be binary kind of perspective. So this matrix network package takes this approach and turns it up to 11. Okay, so now getting to the grid graph, you want to have a grid. So in physics problems, you have some physical space. I'm going to change my screen share to do my PowerPoint. And so can you see, hopefully this GIF is animated.
Yeah, we see the PowerPoint full slide.
But the GIF is not animated.
Nope.
That is unfortunate. So what this GIF is supposed to show is that you have a two-dimensional space, and at each point in the two-dimensional space, there's a concentration of some chemical. And it's a high concentration where it's dark blue, and it's low concentration in light blue. And there's a current. If you saw this GIF, it would push this concentration to the right, and then diffusion would cause it to spread and become dilute. So this is the advection reaction diffusion equation solved over a 2D grid. But you're not seeing the grid. You're not seeing the GIF, so that's not great. But okay, so now we're back in the notebook. So my point was that for physics problems that happen in two-dimensional space, you have you want to specialize on the Laplacian of an integer lattice. So you can define a struct called a grid graph, and you store just two integers, the height and the width, and then you implement the LightGraphs interface for edge type and directed and number of vertices, number of edges, what is the vertex set, and then you can define the edge set as a function. So you can store an arbitrarily large grid with just two integers. And then the edge set is computed dynamically every time you need to access it. The same for out neighbors. It's basically the same, this is the inner loop. This is the body of this loop, basically. Has vertex, has edge. You can just check, is this vertex in the out neighbors? So then you can make a grid graph. This is the 6x6 grid graph. And then show, So you can show, okay, so the 6x6 grid has 36 vertices, 6 times 6, and it has 120 edges, which is approximately 4 times the number of vertices. And so we can do a custom layout. We talked about this when we were talking about graph plots, is that you might want a custom layout where every time I have the grid, I want it to be laid out exactly on the grid. So you calculate, closed form, what's the formula for that layout? And we're going to define a distance color scheme. So we can plot our grid, and we're counting kind of from the bottom left to the top right, row by row, column by column. And then from there, you get, you can just call Dijkstra's shortest path on your graph starting at a vertex and make some plots. Oh, there's all this extra printing is from my debugging statements. Where was my bug? My bug was here in grid layout. These were integers instead of floats. So when it tried to do the layout, it had an inexact error. So I added these extra shows to help me debug that. Get rid of that. There we go. So if you look at the shortest path starting at the first vertex, you see the shortest path tree. So the tree that you get from the Dijkstra's algorithm is shown in the red edges. And then the color is the distance. So if you start here, the darkest one, that's the shortest, and you build your breadth first search tree. And remember that none of these edges are actually stored in the graph. They're created on demand when you do the Dijkstra's shortest path and when you do the plotting. These edges, now the edges exist in the SVG that is produced by Compose, but they aren't in the LightGraphs isn't materializing these edges. You can look at other starting vertices, like somewhere in the center. You kind of see spiraling out the distances. And then, we can define PageRank. And now this PageRank computation is happening with no explicit matrix. It's just using the action of the adjacency matrix is computed by traversing the out neighbors and doing all the math implicitly. And so then you can see kind of the corners are the least central, and the middle is it's a uniform grid here. So this is why when we talked about the spectral layout for the grid, and I said, oh, the boundary is special because it has a different number of neighbors. Here in PageRank, that same artifact shows up where the boundary, like the corners only have two neighbors, so they're the least central. The boundaries have 3 neighbors, so they're less central, and the interior points have 4 neighbors, so they're the most special. That, and then you can do like cross-goal MST and get a minimum spanning tree here. That's kind of fun. Like the column. So if you want a tree that spans this graph, now all the edge weights are the same. So minimum is, it's not really minimum in any sense. So the MST though, it's all the columns and then one of the rows, and that spans the whole grid. So yeah, so that's how you can define a custom graph type. I think the benefits here are if you have some computational workload you're doing and you need to specialize the algorithms to take advantage of that. If your graph is planar or your graph is highly regular, like lattices and triangulations and meshes, you can specialize and go faster. Or if you have a storage medium, you could do the same thing. So if you wanted to do research into distributed graph algorithms, you could have a distributed graph that stored the adjacency matrix as a distributed array. And then you'd have to overload functions to operate correctly. You have to use distributed memory algorithms because the default algorithms will actually just centralize all the data onto the main node. But anyway, you can very easily extend LightGraphs with your own custom graph types and selectively implement more and more of the library to specialize and exploit the structure. And I think that's, especially for people working in scientific computing, a big part of scientific computing is this kind of, if I know more about the problem, I can make a faster algorithm that leverages that structure. So that's how you do it for graphs. Oh yeah, and if you want to do some homework, you could do complete graphs and path graphs and do them in place. They're like pretty easy to write down formulas for. So cool. Let's maybe do some more questions.
Mm-hmm. And yeah, so now so if you want some solutions to the homework, you can also check Special Graphs itself, which has the solutions for path graph and complete graphs. Not grid graph yet, though.
Right. Yeah. So yeah. So there was the bug fix. Somebody, Emiliano wants us to do intros. Well, we kind of missed the boat there. How do you compare scientific calculation in Julia compared to Python? And then what's the future of LightGraphs? And if you have an error in a package, how does the user know when to update? Okay, so I'll take I'll take the security one is like, that's generally package manager ecosystem stuff. And you gotta, I haven't used a Julia package where there was a security hole yet. Fingers crossed. Mostly because I don't use Julia for like web apps or something where it like interacts with the operating system in a meaningful way, where like security would be a problem. So yeah, that's a question for the package ecosystem developers. For scientific computing, I think that one of the reasons that motivated me to take on Julia as opposed to using Python, which is what I was using before, is the two language problem, where all of your scientific computing libraries in Python are wrappers around C++ or C or Fortran implementations. And Julia is the only programming language where you can write your numerical algorithms in the high-level language and have them be just as fast. And for graphs, kind of GraphPlot is an attempt to fix this. Like you can have NumPy because the BLOS is universal for a certain type of scientific computing. There's no universal set of primitives for graph computation like there is for matrix computation. Kind of anything you can do with a matrix is, you can multiply vectors, you can multiply matrices times vectors, or you can multiply matrices times matrices. And that's kind of the scope of what you can do with a matrix. And every linear algebra algorithm can be written in terms of those operations. But for graph algorithms, that's not really how it works. You can do things with the neighborhoods, you can do things with the edges, you can construct flows, and there's a lot going on in graph theory where there's no set of primitive graph theory computations like there is in the BLOS. So that's why LightGraphs exists, is that you can't just implement, or at least the GraphPlot people are trying to do this, but they're not successful yet, I'd say, in terms of like, I can pick up an arbitrary graph paper, take an arbitrary scientific paper that uses graphs and be like, how do I implement this algorithm in GraphPlot? The software's not that mature yet. It might be a couple years from now, but I think there's always going to be people who want to just write graph algorithms with loops, and they need those loops to be fast. I see, was it persistence of LightGraphs as a graph DB? Yeah, there's no, that's not a thing. That MetaGraphs is the closest thing to a graph database, but it's not, it doesn't support like Sparkle queries or anything like that. Yeah. Matt, are there more questions I should take?
As you wish. So I think another one, I guess, that would be a good conclusion also would be about the future of LightGraph. So Simon mentioned quickly the work in progress for LightGraph 2.0, which is still very speculative at this point. I mean, we're not finished yet before the first release, I guess. But Simon, do you want to add something on that?
I mean, it's mostly Ceph working there at the moment, but yeah, we do a big, I think, overhaul of the interface. I mean, stuff will still kind of look the same, but I think it will be more consistent. Different graph types should work together. Also, we have Abhinav, who also did the GraphPlot wrapper. He's doing the GSOC this summer now, and he's doing more parallel and multi-threaded algorithms, which should be really exciting. Yeah. Yeah, that's basically what I know so far. Future. I mean, personally, I have a lot of ideas, but don't have time for that anyway. So.
Yeah, it's kind of in an open source. It's mature open source software. So like things are gonna get added as people decide to add them. We don't have kind of a large scale, like it works for everybody's use case that they need it to work for, and when they do something that it doesn't work for, they add features. Right? It's not like a constant development cycle where we have a Scrum meeting where we have user stories and stuff like that. Yeah, I think that that's where we are. Cool. Well, thank you for coming to our talk. I can throw my awesome slide up again.
There's still a few questions, so I think we have 10 minutes left. So
yeah, some of them I forgot to take that were already answered, I think. Yeah, we need to fix something apparently in the graph, in the GraphPlot.
some question about our sortativity, but I'm not familiar with the topic.
Sortativity, I'm not sure either. I think this is also a problem that you might use graph to describe and then use jump to formulate and then solve using a solver, I think.
Yeah, there's also a question for exponential random graph models. And yes, we have several random graph modules. We didn't talk about them at all today. Oh, we showed Erdos-Rainy, but yes, there's a stochastic block model interface that I wrote to study spectral clustering. So that's still in there, and that's similar to an exponential random graph model. So that's kind of a, maybe, I don't know if you'd consider it well-designed or poorly designed. It was a novel design when I wrote it a couple years ago. But yeah, that could be extended to arbitrary DRGMs for sure. A really interesting problem or challenge that you tackled with LG. Yeah, I think finishing grad school was the most challenging problem that I tackled using LightGraphs. And you guys are on deck, right? You're finishing up. I won't ask on YouTube how long until your defense mat. But.
Don't make me cry live, please.
You made me debug on the air. So.
Right.
Payback.
A few months, yeah. End of the year, roughly.
Yeah, I think that's the most challenging problem. That doing research is relative to the actual merits of the challenge of the research problem, but the challenge of committing to a project and following through and executing. So yeah, I think people have been involved. The people who've been involved in LightGraphs have been involved for a long time, and so it's a good thing.
Yeah, also there was a question. So yeah, we will definitely update the last notebooks with all the bug fixes, typo fixes, and so on that we had.
Yeah.
I think if there are any questions in the future, I mean, people can still come to the Julia Slack or now to Zulip nowadays, or on the Discord.
So yeah.
Performance or usability improvements for MetaGraphs. That's something on Algebraic Julia we're working on. Kind of a different perspective on MetaGraphs that will cover multigraphs and arbitrary metadata in a more structured way. So I hope some point in the next couple months there's improvements in MetaGraphs.
There's actually some project in the JuliaGraphs repository for some newer version of MetaGraphs, but I have not really checked it.
Yeah. Yep. And then that work also uses GraphViz for drawing. So somebody had asked earlier about GraphViz, and there's something in CatLab that uses GraphViz. So GraphViz is more for like diagrams of graphs rather than kind of graph drawing in the graph theory sense. So it's like for flowcharts and mathematical diagrams and stuff like that. and programming diagrams. So I think they're pretty different targeted audiences. But should be interoperable and stuff. Well, great. I think we can.
We should wrap up there.
We can call it. And thank you guys for coming to the tutorial and for all your great questions. I hope we answered them as well as we could, and that you're satisfied with those answers. And then hit us up on the LightGraphs channel in the Julia Slack, or on the Discord throughout the conference, or on Twitter. I think we're all on Twitter. So that's the best way to get a hold of Matt.
All right. Take care, and see you in the other sessions of the conference.
All right, then.
Yep.
See you guys.
Thank you guys. Bye-bye.
Thanks. Bye.